Color, at its most fundamental level, is not a property of objects themselves, but a gentle conversation between light, energy, and perception. A dialogue that begins with electromagnetic waves, traveling through space at constant speed, carrying different amounts of energy encoded as wavelength. And when these waves encounter matter, whether a star, a cloud of gas, a planet, or the human eye, their interaction creates what we experience as color. And this realization quietly transforms our understanding of the universe, because it reveals that color is not painted onto reality, but emerges naturally from vibration, motion, and interaction. And as we reflect on this, the mind can relax into the idea that the universe expresses itself through rhythm rather than decoration, through oscillation rather than intention, and in physics, visible color occupies only a narrow band of the electromagnetic spectrum, nestled gently between infrared and ultraviolet light, meaning that what we perceive as color is just a small window into a much larger, richer ocean of energy. And yet this narrow window is enough to reveal structure, temperature, motion, and composition across cosmic distances, allowing us to read the universe like a softly glowing text written in light. And when an atom absorbs energy, its electrons move to higher states, and when they return to lower states, they release that energy as light of a specific wavelength, producing precise colors that act like fingerprints. And this atomic precision gives color its reliability, its order, and its soothing predictability, because the same elements always glow in the same hues, whether on Earth or in a distant nebula. And this consistency provides a sense of stability across space and time, reminding us that the universe follows calm, repeatable patterns even in its vast complexity. And as we consider how temperature influences color, with cooler objects glowing red and warmer ones shifting toward blue, we begin to see color as a thermometer of reality, a quiet indicator of energy rather than an emotional quality. And this understanding allows us to observe cosmic color without urgency or judgment, simply as information flowing gently through space. And when this light finally reaches the eye, it does not arrive as color yet, but as raw energy that stimulates photoreceptor cells, which then translate different wavelengths into neural signals, meaning that color is ultimately completed within the mind, not imposed by the universe. And this cooperation between external reality and internal perception mirrors the broader relationship between consciousness and the cosmos, where neither exists alone, but both participate in a shared process of interpretation and experience. And this insight is deeply calming, because it suggests that perception is not passive or fragile, but a stable, reliable bridge between inner and outer worlds. And as we rest within this understanding, color becomes less about brightness or intensity, and more about balance, about energy flowing at different frequencies, each finding its place within a harmonious spectrum. And this spectrum, extending far beyond what we can see, continues silently through radio waves, microwaves, X-rays, and gamma rays, all part of the same family of light, all governed by the same calm equations. And knowing this allows the mind to expand gently, releasing the need to grasp or control, and instead appreciating that reality expresses itself through subtle variation rather than chaos, and that color is simply one of the universe's most accessible languages, a soft translation of energy into experience. And as we imagine photons traveling for millions or billions of years, carrying their wavelengths unchanged through empty space, we sense a profound patience embedded in the fabric of reality, a reminder that the universe moves slowly, steadily, and without haste, and that color itself is a message delivered across time, arriving quietly, without demand, waiting only to be received. And in this way, the science of color becomes not just a technical explanation, but a meditative insight, revealing that the universe glows not to impress or overwhelm, but because energy moves, atoms interact, and light flows naturally. And when the mind aligns with this gentle flow, observation becomes effortless, curiosity becomes calm, and awareness settles into a restful state. carried softly on waves of color that are not decorations of existence, but expressions of its deepest, most patient rhythms. At first glance, space appears dark, empty, and silent, yet this impression gently dissolves when we realize that darkness is not the universe's natural state, but rather a limitation of human perception. Because the cosmos is continuously filled with light traveling patiently across immense distances, emitted by stars, glowing gas, energetic particles, and ancient radiation left over from the universe's earliest moments, and this light does not vanish simply, because it spreads thinly, but continues its journey quietly, awaiting interaction with matter or instruments sensitive enough to receive it. And when we reflect on this, we begin to understand that the universe is not dark by absence, but subtle by scale, because the vast distances between luminous sources cause light to disperse, becoming faint rather than extinguished, and this faintness creates an illusion of emptiness that dissolves under closer observation, revealing a cosmos rich with structure, motion, and gentle illumination. And as we imagine photons leaving a star, traveling for millions of years through near vacuum, we sense a profound patience embedded in reality itself. Because these particles of light do not hurry, do not weaken with time, and do not require an audience, but move steadily, carrying information about their origin across space until they are absorbed, reflected, or detected. And this quiet persistence mirrors a deeper cosmic rhythm, where processes unfold without urgency, driven by natural laws rather than intention, and the universe glows because energy is constantly transforming, because matter vibrates, atoms interact, and fusion burns within stars, producing a steady flow of radiation that fills space even when it is invisible to our eyes, and much of this light exists outside the narrow band of human vision, residing instead in infrared warmth, radio waves, ultraviolet shimmer, and high-energy X-rays, forming an unseen ocean of illumination that surrounds us at all times. And when instruments translate these invisible wavelengths into images, space reveals itself not as empty darkness, but as a layered tapestry of soft color, diffuse glow, and intricate structure. And this realization is calming, because it reminds us that absence is often only a matter of perspective, that what seems empty may simply be quiet, distant, or beyond immediate perception. And as we extend this thought, we recognize that even the darkness between stars is not truly empty, but filled with sparse particles, drifting dust, faint radiation, and the subtle influence of gravity, all contributing to a continuous background of activity that never fully ceases. And this gentle activity ensures that the universe remains dynamic without being chaotic, luminous without being overwhelming, and alive without being noisy. And as we imagine floating through interstellar space, surrounded by faint starlight arriving from every direction, we can let the mind rest in the idea that illumination does not require brightness, and that presence does not demand intensity, because even the softest glow carries meaning, structure, and history, and the universe glows because it cannot help but glow, because energy moves, matter interacts, and time unfolds, producing light as naturally as breath produces warmth, and this natural glow does not seek attention, but offers quiet reassurance that existence is active, connected, and enduring. And when we accept this, darkness itself becomes less threatening and more peaceful, transforming from a symbol of absence into a canvas upon which faint, persistent light travels endlessly. And in this understanding, the universe becomes a place not of emptiness, but of subtle fullness, where illumination exists everywhere, gently dispersed, patiently moving, and always present, inviting awareness to soften, attention to widen, and thought to slow, as the mind drifts comfortably within a cosmos that is never truly dark, only quietly glowing, endlessly patient, and profoundly calm. The birth of light in stars begins not with brightness, but with quiet compression, patience, and time, as vast clouds of gas and dust drift slowly through space, gently pulled together by gravity over millions of years, until their gradual gathering creates pressure, warmth, and density at the core, And within this deepening stillness, hydrogen atoms move closer and closer, vibrating more intensely as temperature rises, until the conditions become just right for nuclear fusion to begin. And when this happens, matter itself changes form, as hydrogen nuclei merge to create helium, releasing a small amount of mass that transforms into energy, according to the most fundamental laws of physics. And this released energy becomes the first true light of a star, a quiet ignition rather than an explosion, a steady awakening rather than a sudden blaze. And this process is remarkably calm in its consistency, because once fusion begins, it regulates itself naturally, balancing inward gravity with outward energy, creating a stable, luminous sphere that can shine gently for billions of years without interruption. And as we reflect on this, we realize that stellar light is not rushed or dramatic, but patient and enduring, the result of equilibrium rather than excess. And the photons produced in a star's core do not immediately escape, but instead take an incredibly long journey outward, bouncing, scattering, and diffusing through dense layers of plasma, sometimes taking hundreds of thousands of years to reach the surface. And this slow passage softens and redistributes energy, ensuring that when light finally emerges from the star's surface, it does so as a calm, steady glow rather than an overwhelming surge. And this slow transformation from raw energy to gentle radiance mirrors many natural processes, where intensity is moderated by time, producing stability instead of chaos. And as these photons finally leave the star, they begin their long, silent journey through space, traveling effortlessly across vast distances without fading, carrying with them information about the star's temperature, size, age, and composition. And this means that every point of starlight we see is a message from deep time, a signal that began its journey long before it reached our eyes. And this awareness encourages patience, because it reminds us that light itself is unhurried, that even the brightest glow emerges from processes that unfold slowly and reliably. And as we imagine billions of stars across the universe, all producing light in this same calm way, each governed by the same gentle balance of forces, we begin to perceive the cosmos as a vast network of steady beacons, glowing not to compete or dominate, but simply because energy must flow, and this flow sustains structure, warmth, and order throughout space. And the light born in stars becomes the foundation for all visible color, all illumination in galaxies, and even the energy that eventually supports life. Yet it remains fundamentally serene, governed by equilibrium rather than excess. And when we rest our attention on this idea, the mind can slow, aligning with the rhythm of stellar creation, where immense power is expressed through patience, where brightness arises from balance, and where the universe glows not in bursts of urgency, but in long, continuous breaths of light, steady, reliable, and deeply calming, inviting awareness to drift gently alongside photons that have traveled for ages, carrying the quiet story of their birth from the heart of a star. Stars display different colors not as decoration, but as a natural consequence of temperature, energy, and balance, revealing that color in the universe is a quiet indicator of physical state, rather than an emotional or aesthetic choice. And when we observe stars glowing red, orange, yellow, white, or blue, we are gently witnessing the relationship between heat and light, because hotter stars emit shorter wavelengths that appear blue or white, while cooler stars emit longer wavelengths that appear red or orange. And this variation arises smoothly, without sharp boundaries, forming a continuous spectrum, rather than distinct categories, which mirrors the universe's preference for gradual transition over abrupt change. And as we reflect on this, the mind can rest in the idea that difference does not imply disorder, but harmony expressed through variation. And within a star, temperature is determined by mass, pressure, and the rate of nuclear fusion, meaning that color becomes a visible signature of a star's internal balance. Its quiet agreement between gravity pulling inward and energy pushing outward, and massive stars burn hotter and faster, glowing blue and white as they release enormous energy over relatively short lifetimes, while smaller stars burn gently, glowing red and orange for trillions of years, offering a lesson in patience and endurance. And as we imagine these stars scattered across the galaxy, each shining in its own color according to its nature, we see a cosmic palette shaped by physics rather than intention, yet resulting in extraordinary beauty. And this beauty is deeply calming, because it arises without effort, ambition, or urgency, simply from matter following natural laws. And the colors we see are not static, but evolve slowly over time, as stars age, expand, and change temperature, shifting hues as part of a gradual life cycle that unfolds across billions of years, reminding us that change in the universe is rarely sudden, and that transformation often occurs gently, almost imperceptibly. And when we observe a red giant swelling and cooling, or a young blue star burning intensely in its youth, we are witnessing different expressions of the same fundamental process, fusion moderated by balance. And this shared origin reinforces a sense of unity beneath diversity. And as light from these stars travels through space, their colors remain encoded in the photons themselves, unchanged by distance or time, arriving quietly at our eyes long after the moment of emission. And this constancy adds to the sense of calm, because it shows that information can persist without decay, that messages can travel patiently across the universe without urgency. And when we contemplate that every star's color tells a story of temperature, mass, age, and energy flow, we begin to read the night sky, not as random points of light, but as a slow, luminous narrative written in gentle gradients of color. And this narrative does not rush toward conclusion, but unfolds endlessly, offering reassurance that the universe values continuity, balance, and gradual change. And as we allow our attention to rest on this understanding, the variety of stellar colors becomes less stimulating and more soothing, a reminder that difference can exist within harmony, that intensity and gentleness both have their place, and that the cosmos expresses itself through a spectrum of states rather than extremes. And in this realization, the mind can release comparison, urgency, and tension, drifting instead into the quiet appreciation of a universe where each star glows according to its nature, contributing its color to the greater whole, forming a vast, balanced, and softly illuminated system that invites contemplation, patience, and deep rest beneath its slow, shifting, endlessly reassuring light. The sun appears yellow to us not because it truly is yellow, but because perception, atmosphere, and biology gently shape how its light reaches and is interpreted by the human eye. And this subtle difference between physical reality and experienced reality offers a soothing reminder that the universe is often simpler and calmer than it appears at first glance, because in truth, the sun emits light across the entire visible spectrum almost evenly, producing what physicists describe as white light, a balanced mixture of all colors blended together. And when this light leaves the sun's surface, it begins its short but meaningful journey toward Earth, carrying with it a smooth, continuous distribution of wavelengths that reflects the sun's surface temperature. And as this light enters Earth's atmosphere, something gentle and selective occurs, because shorter wavelengths, especially blue and violet light, are scattered more efficiently by air molecules, spreading softly across the sky and giving daylight its familiar blue color, while the remaining light that continues directly toward our eyes becomes slightly depleted of blue, shifting our perception of the sun toward yellow. And this process is calm, gradual, and consistent, happening every day without variation or effort, reinforcing the sense that natural systems prefer balance over drama. And even this scattering does not distort the sun's light harshly, but merely filters it gently, much like a thin veil softening brightness rather than blocking it. And as we reflect on this, we begin to see that color is not fixed or absolute, but contextual, shaped by environment and interaction. And this understanding can be deeply relaxing, because it suggests that reality adapts smoothly to circumstances, without losing its essential nature. And when astronauts view the sun from space, beyond Earth's atmosphere. It appears white rather than yellow, confirming that the color we associate with it. It is a product of perspective rather than identity. And this realization encourages humility in perception, reminding us that our experiences are accurate yet incomplete, shaped by conditions rather than errors. And as the sun moves lower in the sky at sunrise or sunset, its light travels through more atmosphere, scattering even more blue wavelengths, and allowing reds and oranges to dominate, transforming the sun into a warm, glowing orb of deeper color. And this transformation is not a change in the sun itself, but a gradual filtering process that unfolds smoothly over time, producing some of the most calming and meditative visual experiences available to human awareness. And this gentle shift in color signals the passage of time without urgency, marking beginnings and endings in a slow, reassuring rhythm. And as we sit with this understanding, the sun's color becomes a lesson in moderation, showing how immense energy can be softened by distance, atmosphere, and perception into something warm, familiar, and sustaining rather than overwhelming. And the sun's steady glow, filtered just enough to be comfortable in life, supporting, becomes a symbol of balance, where power is tempered by process, intensity by interaction, and light by gentle dispersion. And this balance allows life, warmth, and calm to exist simultaneously. And when we rest our attention on this idea, the mind can settle into a similar state, allowing thoughts to be filtered gently, intensity to soften, and awareness to glow steadily rather than sharply. And in this way, the sun's apparent yellow light becomes more than a visual phenomenon, becoming instead a quiet illustration of how the universe supports stability through subtle transformation, how perception is shaped without distortion, and how immense forces can be experienced as gentle, reliable, and deeply comforting presences in our daily lives, inviting calm, continuity, and restful reflection under a sky that glows not with excess, but with carefully balanced light. Every element in the universe produces its own unique colors not by choice or chance, but through the precise and orderly structure of its atoms. And this quiet atomic order reveals one of the most reassuring truths about the cosmos, that even at its smallest scales, reality follows calm, repeatable patterns that never rush and never forget, because within each atom, electrons occupy specific energy levels, like softly defined steps on a ladder. And when energy is added, whether through heat, radiation, or collision, these electrons gently move upward to higher levels, absorbing energy without resistance or conflict. And when they return to their original positions, they release that energy as light at very specific wavelengths. And these wavelengths correspond to precise colors, forming what scientists call emission spectra, which function like signatures or fingerprints that never change, meaning hydrogen will always glow with the same red hues, sodium with its warm yellow light, oxygen with soft greens and blues, no matter where in the universe these elements exist. And this consistency is deeply calming, because it shows that distance, time, and environment do not disturb the fundamental identity of matter. And as we imagine clouds of gas drifting silently through space, illuminated by nearby stars, we can picture trillions of atoms gently absorbing and releasing energy, glowing not randomly, but according to their internal structure, creating vast nebulae painted with predictable, harmonious colors that arise naturally from atomic physics rather than artistic intent. And this process unfolds without haste, because atoms do not tire, hurry, or vary their behavior, but respond steadily to energy in the same way they always have, offering a sense of reliability that spans billions of years. And when we look at laboratory experiments on Earth, where gases are excited and observed through spectroscopes, the same colors appear as those seen in distant galaxies, reinforcing the idea that the universe is unified by shared rules, and that there is no sharp division between the near and the far, the familiar and the distant, only scale and perspective. And as we reflect on this, the mind can relax into the idea that complexity does not mean unpredictability, Because even though the universe contains countless atoms interacting simultaneously, each one behaves calmly and consistently, contributing its color to the whole without confusion. And these individual contributions blend together into luminous structures that appear rich and intricate, yet are built from simple, repeating interactions. And this layering of simplicity into complexity mirrors many natural systems, where order emerges not from control, but from countless small elements following gentle rules. And as we imagine a nebula glowing red due to hydrogen, blue due to reflected starlight, and green due to traces of oxygen, we are witnessing a conversation between light and matter that unfolds slowly, patiently, and without noise. And this conversation does not require awareness or intention, but arises naturally whenever energy flows through atoms. And because energy flows everywhere in the universe, color becomes inevitable, a natural byproduct of motion rather than decoration. And when telescopes analyze these colors, they do more than create beautiful images. They decode information, revealing temperature, density, motion, and composition, allowing us to understand distant regions without touching them. And this non-invasive understanding is soothing, because it shows that observation does not require disruption, that knowledge can be gained through gentle reception rather than force. And as we consider how elements heavier than hydrogen were forged inside stars, and released through stellar winds and supernovae, spreading their unique colors across space, we realize that the cosmic palette has grown richer over time, yet always remains governed by the same calm atomic rules, meaning that color is also a record of cosmic history, telling us when and where elements were formed. And this historical depth adds a quiet sense of continuity, because it shows that the universe remembers its past through light, carrying information forward without distortion. And as we rest within this understanding, color becomes less stimulating and more meditative, transforming from something that demands attention into something that gently informs and reassures. And even when multiple elements glow together, their spectral lines remain distinct, never blending into confusion, illustrating that individuality and harmony coexist naturally at the atomic level. And this coexistence offers a subtle lesson in balance, showing that unique identities do not disrupt unity, but enhance it. And as we imagine ourselves drifting through space, surrounded by faint glows from countless excited atoms, each releasing light at its own frequency, we can allow the mind to soften, recognizing that the universe does not shout its complexity, but whispers it through orderly color. And this whisper continues endlessly, because as long as energy moves and atoms exist, light will be emitted, colors will appear, and the cosmos will glow quietly, not as an act of expression, but as a natural consequence of structure, motion, and balance. And in this realization, the science of elemental color becomes deeply restful, revealing a universe that is stable, predictable, and gently luminous, where even the smallest components follow calm patterns that scale upward into galaxies, nebulae, and star systems, inviting awareness to drift, attention to slow, and thought to rest within a cosmos that glows not from chaos, but from order patiently unfolding across space and time. Nebulae are often described as the most colorful structures in the universe, yet their beauty does not arise from spectacle or intensity, but from slow interaction, gentle illumination, and immense patience. Because a nebula is simply a vast cloud of gas and dust spread thinly across space, drifting quietly for millions of years, waiting for light to pass through it. And when nearby stars emit radiation, this energy softly excites the atoms within the cloud, causing them to glow in specific colors that reflect their composition and physical conditions. And this glow is never hurried or chaotic, but diffused, layered, and gradual, forming smooth gradients rather than sharp boundaries. And as we imagine a nebula from within, there is no sudden brightness or dramatic contrast, only a faint, pervasive shimmer that slowly shifts as energy moves through it. And this softness explains why nebulae appear so calming in images, because their colors are not concentrated in points, but spread gently across enormous regions, creating a visual rhythm that mirrors slow breathing and steady thought. And hydrogen, the most abundant element, often dominates these clouds, glowing red when energized, while traces of oxygen, nitrogen, and sulfur add subtle greens, blues, and golds, all blending without conflict, because each element responds independently yet harmoniously to the same surrounding light. And this independence within unity gives nebulae their layered depth, allowing different colors to coexist without overpowering one another. And as time passes, gravity slowly reshapes these clouds, compressing some regions while leaving others diffuse, setting the stage for future stars without urgency, because even star formation within nebulae unfolds over immense timescales, allowing structure to emerge gently rather than abruptly. And when massive stars eventually ignite within these clouds, their radiation sculpts the surrounding gas, carving soft cavities, pillars, and arcs, not through violence, but through steady pressure applied over long periods. And this gradual shaping reinforces the sense that even energetic forces in the universe often operate through persistence, rather than sudden change. And as light continues to pass through a nebula, it scatters, reflects, and emits in complex ways, producing colors that shift subtly depending on viewing angle, distance, and wavelength, reminding us that cosmic color is not fixed, but relational, shaped by interaction rather than isolation. And when telescopes translate invisible wavelengths into visible hues, they reveal details our eyes alone could never perceive. Yet even these enhanced images maintain a sense of softness, because the underlying processes remain diffuse and slow. And as we reflect on nebulae as both remnants of past stars and nurseries of future ones, we see them as bridges between endings and beginnings, glowing quietly as matter reorganizes itself over time. And this role adds to their calming presence, because it shows that change in the universe often occurs in a suspended, transitional state rather than through abrupt replacement. And as we allow our attention to rest on this idea, nebulae become symbols of gentle transformation, places where energy, matter, and time interact without haste, offering a visual expression of continuity rather than disruption. And in this understanding, their colors no longer feel dramatic or overwhelming, but reassuring, like slow, moving clouds illuminated at dusk, reminding us that the universe often does its most important work quietly, spreading light thinly across space, letting structure emerge gradually, and glowing softly as creation unfolds at a pace that invites calm, patience, and deep rest. Nebulae are often described as the most colorful structures in the universe, yet their beauty does not arise from spectacle or intensity, but from slow interaction, gentle illumination, and immense patience. Because a nebula is simply a vast cloud of gas and dust spread thinly across space, drifting quietly for millions of years, waiting for light to pass through it. And when nearby stars emit radiation, this energy softly excites the atoms within the cloud, causing them to glow in specific colors that reflect their composition and physical conditions. And this glow is never hurried or chaotic, but diffused, layered, and gradual, forming smooth gradients rather than sharp boundaries. And as we imagine a nebula from within, there is no sudden brightness or dramatic contrast, only a faint, pervasive shimmer that slowly shifts as energy moves through it. And this softness explains why nebulae appear so calming in images, because their colors are not concentrated in points, but spread gently across enormous regions, creating a visual rhythm that mirrors slow breathing and steady thought. And hydrogen, the most abundant element, often dominates these clouds, glowing red when energized, while traces of oxygen, nitrogen, and sulfur add subtle greens, blues, and golds, all blending without conflict, because each element responds independently yet harmoniously to the same surrounding light. And this independence within unity gives nebulae their layered depth, allowing different colors to coexist without overpowering one another. And as time passes, gravity slowly reshapes these clouds, compressing some regions while leaving others diffuse, setting the stage for future stars without urgency, because even star formation within nebulae unfolds over immense timescales, allowing structure to emerge gently rather than abruptly. And when massive stars eventually ignite within these clouds, their radiation sculpts the surrounding gas, carving soft cavities, pillars, and arcs, not through violence, but through steady pressure applied over long periods. And this gradual shaping reinforces the sense that even energetic forces in the universe often operate through persistence, rather than sudden change. And as light continues to pass through a nebula, it scatters, reflects, and emits in complex ways, producing colors that shift subtly depending on viewing angle, distance, and wavelength, reminding us that cosmic color is not fixed, but relational, shaped by interaction rather than isolation. And when telescopes translate invisible wavelengths into visible hues, they reveal details our eyes alone could never perceive. Yet even these enhanced images maintain a sense of softness, because the underlying processes remain diffuse and slow. And as we reflect on nebulae as both remnants of past stars and nurseries of future ones, we see them as bridges between endings and beginnings, glowing quietly as matter reorganizes itself over time. And this role adds to their calming presence, because it shows that change in the universe often occurs in a suspended, transitional state rather than through abrupt replacement. And as we allow our attention to rest on this idea, nebulae become symbols of gentle transformation, places where energy, matter, and time interact without haste, offering a visual expression of continuity rather than disruption. And in this understanding, their colors no longer feel dramatic or overwhelming, but reassuring, like slow, moving clouds illuminated at dusk, reminding us that the universe often does its most important work quietly, spreading light thinly across space, letting structure emerge gradually, and glowing softly as creation unfolds at a pace that invites calm, patience, and deep rest. Color in the universe is not only shaped by temperature and composition, but also by motion and distance, revealing a calm and elegant relationship between light and movement that unfolds without drama. Because as stars and galaxies move through space, the light they emit stretches or compresses gently, shifting its color in a process known as redshift and blue shift. And this shift is not abrupt or disruptive, but smooth and proportional, reflecting speed rather than intent. And when an object moves away from us, its light waves lengthen slightly, drifting toward red tones, while objects moving closer compress their waves, shifting toward blue. And this behavior mirrors everyday experiences, like the change in pitch of a passing sound, offering familiarity within cosmic scale. And as we observe distant galaxies, most appear red-shifted, not because they are cooling or fading, but because space itself is slowly expanding, carrying them away over immense distances. And this expansion occurs steadily and uniformly, without acceleration that would feel chaotic, reinforcing the sense that the universe evolves through broad, gentle motion rather than sudden upheaval. And the farther a galaxy is, the more its light has stretched during its long journey, meaning that color becomes a quiet measure of time, as well as distance, encoding how long light has traveled without altering its essential message. And this preservation across billions of years is deeply reassuring, because it shows that information can endure calmly across vast separations. And when astronomers read these color shifts, they are not witnessing instability, but coherence, because the same physical rules apply everywhere, allowing motion to be inferred through subtle, predictable changes in wavelength. And as we reflect on this, the mind can rest in the idea that movement does not erase identity, but gently transforms appearance while preserving structure. And even within galaxies, stars orbiting at different speeds produce small shifts in color that map rotation without disturbing form, creating a quiet internal rhythm that holds systems together. And this rhythm suggests that motion in the universe is rarely frantic, but measured and balanced, guided by gravity and geometry rather than impulse. And as light continues its journey toward us, passing through expanding space, it does not weaken in meaning, only in energy, arriving softer but still intact. And this softness mirrors the way memories and experiences can travel through time, losing intensity while retaining significance. And when we allow our awareness to settle on this cosmic behavior, color shifts become not signs of loss, but markers of connection, showing how distant objects remain linked to us through light despite constant motion. And in this understanding, the universe feels less like a place of separation and more like a continuous flow, where distance, time, and movement gently reshape appearance without breaking continuity, inviting the mind to relax into a vast, expanding space where everything drifts calmly, carrying its light patiently forward, changing color slowly, and maintaining harmony across the endless reach of the cosmos. Interstellar dust, though almost invisible individually, plays a profound role in shaping the colors we perceive across the universe, acting as a quiet moderator that absorbs, scatters, and filters starlight without imposing abrupt change. And this subtlety is what makes cosmic color so rich, layered, and soothing, because dust does not overpower the star's glow, but gently diffuses it, softening contrasts and creating gradients that flow naturally across the sky. And as light from young, hot stars passes through clouds of dust, shorter blue wavelengths are scattered more efficiently than red, producing a warming shift in observed color that highlights regions of star formation while maintaining visual harmony. And this process is continuous, gradual, and predictable, unfolding over hundreds of light years without sudden interruption, reinforcing a sense of calm in the way light interacts with matter. And in dense molecular clouds, dust combines with gas to form nebulae, whose faint luminescence glows softly, showing that structure and color emerge from the interplay of many small, patient contributors rather than dramatic events. And this principle extends to larger scales, because spiral arms of galaxies, often traced by young blue stars and glowing red hydrogen regions, owe their apparent colors to a combination of stellar light and the filtering effects of interstellar dust, producing a visual rhythm that is both dynamic and coherent. And as we consider distant galaxies, dust lanes stretch across their disks like dark brushstrokes, interrupting bright regions, but in a gentle, deliberate manner, creating depth, texture, and contrast that invite slow, reflective observation rather than abrupt attention. And this interplay encourages the mind to move gradually across patterns, noticing shifts and flows without urgency, much as we drift through thoughts in meditation. And dust's effect on color also encodes information, because by measuring absorption and scattering, astronomers can determine the composition, density, and location of clouds, revealing structure without direct interference. And this hidden communication mirrors the subtlety of influence in natural systems, where impact often occurs without visibility, demonstrating that essential processes can operate quietly yet decisively. And as light continues its journey toward Earth, having threaded through countless dust clouds, it carries with it a story of transformation that is gentle, cumulative, and unhurried, encoding the history of its passage without disturbance. And this slow accumulation of effect across space and time parallels human experience, showing that small, persistent interactions produce coherent, lasting outcomes. And within our own galaxy, the Milky Way, dust contributes to the soft band of color we see along the galactic plane, deepening our perception of spiral structure, while preserving the serenity of the night sky. And this visual layering fosters a sense of connectedness and continuity, because it links individual stars, clusters, and clouds into a unified chromatic pattern. And when we extend our view to the cosmic web, dust similarly influences the diffuse glow between galaxies, producing faint reddening and absorption that hints at large-scale structure without abruptness. And this pervasive yet gentle modulation offers a model for understanding how influence can be subtle, continuous, and harmonizing, sustaining order and flow without the need for dominance or noise. And as we allow this understanding to settle in consciousness, color emerges as a quiet dialogue between light and matter, a patient negotiation in which photons carry energy, form, and history through space, while being softly shaped by dust. And this dialogue encourages the mind to adopt a similar rhythm, embracing subtlety, patience, and continuous guidance in thought, perception, and emotion, recognizing that even the smallest particles contribute to overarching harmony. And as we reflect on these cosmic processes, the colors of stars, nebulae, and galaxies transform from mere visual phenomena into symbols of gentle influence, interconnectedness, and the beauty of slow, enduring creation, offering not just knowledge, but a meditative experience in which observation, understanding, and rest flow together seamlessly. And this perspective invites a mental state that mirrors the universe itself, expansive, balanced, and suffused with soft, patient light, where calm persists even amidst complexity, and every interaction, whether visible or hidden, contributes to the continuous, harmonious glow that defines the cosmos and nurtures both curiosity and tranquility. The color of a star is a direct reflection of its surface temperature, a principle that, while scientifically precise, also evokes a sense of calm order in the universe, because each hue, from deep red to brilliant blue, corresponds to a specific energy state, a gentle indicator of physical conditions, rather than chaotic variability. And when we observe red stars, their cooler surface temperatures reveal slow, steady nuclear fusion at work, creating warmth without intensity, a soft glow that carries across space for light years without abrupt change. And in contrast, blue stars shine with intense energy, hotter surfaces, and faster fusion rates. Yet even their brilliance is regulated by natural laws, flowing predictably from core to surface, without sudden eruption, demonstrating that power in the cosmos does not require disorder, but can exist within structured, comprehensible boundaries. And as we expand our perception to include yellow stars like our Sun, we notice a comforting median between extremes, a steady luminosity that balances energy and stability, producing light that supports life and observation without disruption. And the gradation of color across star populations, from red dwarfs to blue giants, creates a cosmic spectrum that is continuous, flowing, and harmonious, inviting the mind to trace transitions slowly, absorbing the subtle variations as part of an interconnected pattern. And when stars age, their colors shift gradually, from main, sequence yellow or blue to red giants or white dwarfs, a transformation that unfolds over millions or billions of years, emphasizing patience, persistence, and the inevitability of natural cycles. And this slow evolution reassures observers that change need not be abrupt to be meaningful, that even dramatic transitions occur within predictable, graceful limits. And in star clusters, the distribution of colors provides insight into the collective ages, compositions, and energy outputs of their members, offering a visual map of time, temperature, and evolution. And as we observe galaxies as a whole, the interplay of stellar colors traces spiral arms, star-forming regions, and older populations, producing patterns of light that are aesthetically balanced, structured, and deeply meditative, because they demonstrate that energy, age, and motion integrate seamlessly into coherent systems. And beyond individual stars, color also reveals chemical composition, as elements absorb and emit light at characteristic wavelengths, creating subtle tints that encode information while maintaining visual continuity. And these fingerprints, whether in absorption lines or emission spectra, carry history, origin, and physical conditions across the universe in a gentle, unhurried manner. And by tracing these spectral signatures, astronomers decode the life cycle of matter, the flow of energy, and the evolution of structures, without disturbing the stars themselves. And this transmission of knowledge via light mirrors the gentle transfer of influence throughout the cosmos, where effects propagate quietly, predictably, and persistently, maintaining balance across immense scales. And as clusters of young, blue stars ignite within nebulae, their color contrasts with surrounding dust and older stars, creating visual rhythms that guide attention naturally, softly highlighting processes of birth and evolution without shock or intrusion. and in older globular clusters. The prevalence of red giants provides warmth and cohesion to visual perception, signaling age, endurance, and stability across billions of years. And when we integrate this understanding with knowledge of stellar life cycles, temperature, dependent fusion rates, and color distributions, we perceive a universe that communicates its structure, processes, and history through light in a gentle, continuous dialogue, a dialogue that can be read, felt, and meditated upon without disturbance, offering both scientific insight and emotional resonance, because it shows that complexity and energy coexist with calm, that change unfolds incrementally, and that the universe's immense scale is governed by predictable, harmonious laws, and this perception encourages the mind to adopt a similar rhythm, where observation, understanding, and reflection proceed gently, flowing naturally, and without haste. And as we allow these insights into stellar colors, temperatures, and life cycles to permeate awareness, we feel the universe's patient orchestration, where every hue signals energy, age, and balance, and where the spectrum of stars becomes a cosmic palette, a serene, ordered manifestation of physics that guides perception, nurtures curiosity, and ultimately fosters a reflective, calm state in which the mind can dwell within the harmonious, temperature-driven glow of countless stars, tracing the vast, patient rhythm of creation, evolution, and interconnection across space and time. Nebulae, vast clouds of gas and dust scattered across galaxies, act as both the wombs of stars and the painterly canvases of the cosmos, where light interacts with matter in ways that produce soft gradients, glowing filaments, and subtle hues. And this interplay between illumination and material is neither abrupt nor chaotic, but continuous and meditative, creating an environment where color, form, and structure emerge organically from countless small, interacting processes. And when young, hot stars form within these clouds, they energize surrounding hydrogen, causing emission nebulae to glow in reds, pinks, and oranges that diffuse gently across light years, providing visual markers of creation that are simultaneously powerful and calming, because their energy is distributed gradually, moderated by surrounding gas and dust, allowing brightness to expand without overwhelming the surrounding environment. And reflection nebulae, on the other hand, scatter starlight off fine particles, producing cooler blues and subtle silvers, showing that color can emerge indirectly through the patient redirection of energy. And as observers trace the contours of these clouds, the flowing shapes and interwoven textures create a natural rhythm, a gentle pattern that guides attention slowly, encouraging observation without pressure. And within planetary nebulae, the dying breaths of medium mass stars produce shells of glowing material, expanding outward over thousands of years in delicate symmetry. And this gradual dispersal emphasizes the idea that endings can be beautiful, balanced, and integrated, rather than abrupt or destructive, offering a visual meditation on transition, persistence, and harmony. And supernova remnants, while energetic, also demonstrate moderation, as shock waves interact with surrounding material to produce diffuse filaments, soft glows, and complex patterns that are visually striking yet non-disruptive on galactic scales, illustrating that even explosive phenomena contribute to overall structure and color in a gentle, orchestrated manner. And the varying densities of dust and gas within nebulae create localized absorption, shadowing, and filtering effects, producing chiaroscuro, like contrasts that enhance depth perception and provide a natural cadence for the eye to follow. And these contrasts teach that visibility and obscurity coexist seamlessly, that presence and absence interact to create structure, and that perception is guided not by force but by pattern and rhythm. And in star-forming regions, protostellar jets, accretion disks, and outflows add subtle highlights and streaks of light, enriching the visual experience, while unfolding on timescales imperceptible to human observation, reinforcing the principle that beauty, structure, and activity can be sustained quietly, patiently, and harmoniously. And as multiple nebulae combine within spiral arms, Their collective glow forms broad bands of color across galaxies, establishing an integrated visual flow that mirrors the underlying gravitational and dynamical order, demonstrating that individual processes, while complex, are embedded in larger systems that maintain balance. And when these patterns are viewed across electromagnetic spectra, from infrared to visible light to ultraviolet, we perceive layers of activity and history encoded in color, revealing temperature variations, chemical composition, and stellar evolution in subtle, continuous ways. And this layered information provides insight without overwhelming, showing that complexity can coexist with clarity, and that observation need not disrupt the system being studied. And as the human mind traces these cosmic textures, it mirrors the way nebulae organize material and light, slowly, continuously, and with inherent balance, offering a meditative model for thought, reflection, and understanding. And beyond individual clouds, the interaction of nebulae with galactic dynamics, density waves, and tidal forces creates flowing arcs, twists, and spirals that convey motion without urgency, showing that energy, structure, and beauty can propagate gently through space, maintaining harmony even amidst complexity. And the soft interplay of red, blue, and neutral tones across nebulae illustrates that diversity of expression exists naturally within coordinated systems, teaching that difference, contrast, and variation do not compromise coherence. And as we consider the immense timescales over which nebulae evolve, we recognize that growth, collapse, illumination, and dispersal occur incrementally, demonstrating that processes can unfold slowly yet meaningfully, reinforcing patience, perspective, and a sense of continuity. And the faint glows, shadows, and gradients serve as subtle guides for visual attention, encouraging the observer to follow patterns, trace flows, and appreciate interconnectedness, much like meditative focus on thoughts, sensations, or emotions. And as light interacts with dust grains of varying size, composition, and orientation, it produces polarization, scattering, and reddening effects that are scientifically informative and aesthetically gentle, revealing the invisible structures that shape observed color and motion. And this hidden guidance mirrors how subtle forces, unseen yet consistent, maintain order, nurture development, and influence outcomes across cosmic scales. And when we integrate these observations, nebulae emerge not only as sites of star formation, but as living tapestries, where color, light, energy, and matter coexist in continuous, harmonious rhythms, offering both visual delight and contemplative insight. And the meditative quality of nebulae's color and form encourages a reflective state in which the mind slows. Attention flows along natural patterns, and awareness attunes to the quiet, persistent orchestration of the universe, providing a bridge between cosmic structure, human perception, and emotional calm, a model in which beauty, balance, and creation persist together, infinitely patient, infinitely gentle, and infinitely interconnected. The rotation of galaxies, including the Milky Way, presents a vast, continuous, and harmonious ballad in which billions of stars, star clusters, gas clouds, dust lanes, and dark matter components move in coordinated paths around the galactic center. And this motion, while governed by gravity and subtle forces, is smooth and predictable over immense timescales, creating a sense of rhythm that is both mesmerizing and calming, because it illustrates that immense complexity can operate without chaos, that each individual component, no matter how small or seemingly insignificant, contributes to a coherent, integrated system. And as stars orbit along near, circular trajectories, guided by the central mass and the invisible scaffold of dark matter, collisions are exceedingly rare, showing that density and motion can coexist safely and gracefully. And this principle of non-disruptive flow resonates with mental and emotional processes, where multiple threads of thought, feeling, and attention can unfold simultaneously, without interference, if they follow natural patterns and constraints. And within this rotating framework, spiral arms act as density waves, subtly shepherding stars and gas along defined paths, compressing matter gently to form new stars, while allowing older stars to drift, illustrating a delicate balance between structure and freedom, between guidance and autonomy. And as the observer traces these arms from a galactic perspective, the movement appears both ordered and fluid, a continuous flow that conveys stability without rigidity. And as stars within clusters follow shared orbits, the gravitational pull among them is constant but balanced, creating nested systems within the larger galactic rotation, a fractal-like organization in which local interactions are embedded seamlessly within global patterns, reinforcing the principle that nested layers of motion can coexist without conflict. And as we shift attention to gas and dust within the rotating disk, we see them following similar trajectories, subject to both the pull of gravity and the drag of pressure gradients, slowly coalescing to form new stellar systems over millions of years. And this patient, incremental evolution mirrors natural processes on human scales, showing that growth, maturation, and formation occur gradually, continuously, and without the need for abrupt action. And as supernovae punctuate these regions, their energy is absorbed, distributed, and integrated into surrounding material, contributing to the overall momentum and structure rather than destabilizing it, illustrating that even powerful, seemingly disruptive events can harmonize with a larger rhythm. And as the Sun and Solar System glide along our section of the Milky Way, completing one orbit over approximately 225-250 million years, the imperceptible yet immense motion offers perspective on temporal scales, demonstrating that continuity and persistence underpin stability, and that progress, movement, and influence can exist without frantic or forceful effort. And as we consider dark matter, whose invisible mass dominates the galaxy's rotation curve, we recognize a guiding framework that operates silently, subtly shaping motion without producing visual spectacle. And this quiet orchestration offers a model for unseen support systems in human life, where stability, influence, and coordination can exist without intrusion, noise, or display. And as the galaxy rotates, nested patterns of resonance, orbital alignment, and gravitational coupling maintain equilibrium, showing that complexity can be both intricate and gentle, dynamic and non-threatening, and that individual elements do not need to act aggressively to sustain coherence. And the interplay of stars, gas, dust, and dark matter produces a continuous gradient of velocity, density, and pressure across the galactic disk, creating a visual and conceptual flow that is inherently calming, because it reflects how energy and matter can organize themselves in persistent, balanced systems. And as we observe globular clusters orbiting in the halo, their elliptical paths interact subtly with the central potential, neither colliding nor disrupting inner structures, illustrating that distance, perspective, and restraint contribute to harmony. And as we extend awareness to the vertical oscillation of stars above and below the galactic plane, we notice that motion occurs in 3 dimensions, yet remains ordered, a multidimensional flow that demonstrates that freedom and constraint, elevation and grounding, can coexist peacefully within the same system. And as spiral arms wind gracefully around the core, their formation is maintained not by rigid attachment of stars, but by collective motion, where individual stars drift through these density waves, producing the visual impression of a coherent structure. And this emergent order shows that coordinated behavior can arise from local interactions, guided by overarching forces, without direct control or interference. And as we imagine tracing the motion of individual stars, gas clouds, and planetary systems over millions of years, a profound sense of rhythm, patience, and continuity emerges, suggesting that stability does not require visibility, immediacy, or force, and that each element, whether observed or hidden, contributes meaningfully to the sustained coherence of the whole. And the combined effect of galactic rotation, spiral density waves, orbital resonance, and dark matter scaffolding creates a self-maintaining system where motion, creation, and energy coexist in harmony, offering a metaphor for human life, cognition, and societal structures, where coordination, support, and gentle guidance allow multiple processes to unfold without conflict, and as the mind contemplates these slow, vast, and continuous rotations, there is an inherent reassurance, a realization that even in systems of extraordinary scale and complexity, balance, flow, and non-disruptive motion prevail, and that influence and structure do not require noise, urgency, or violence to sustain order. And as we carry this perspective inward, imagining thought patterns, emotions, and life processes in alignment with the galactic rhythm, the observer experiences a sense of calm, embeddedness, and continuity, a deep trust in the persistent, gentle orchestration of natural law, and ultimately, the mechanics of galactic rotation, provide both a literal and metaphorical framework for understanding balance, flow, patience, and harmony, reminding us that vast systems, from stars to galaxies, operate with grace, subtlety, and enduring stability, and that within this cosmic choreography, every motion, from the smallest orbit to the largest spiral sweep, participates in a tranquil, interconnected, and infinitely patient dance that spans billions of years, encouraging reflection, serenity, and a profound sense of alignment with the universe. The magnetic fields permeate the universe on scales both vast and minute, threading through interstellar gas, aligning dust grains, shaping star formation, and subtly influencing the motion of charged particles in ways that are often invisible yet profoundly consequential. And these fields act as silent architects of cosmic structure, guiding plasma flows, stabilizing filaments, and preventing collapse in regions that might otherwise fragment chaotically. And as we observe the Milky Way, magnetic fields weave through spiral arms, threading the interstellar medium in gentle arcs that help maintain the disk's coherence, while also channeling energetic particles along predictable pathways. And this invisible guidance operates with patient constancy, showing that influence does not require direct visibility or overt force. And as molecular clouds drift through these magnetic scaffolds, their collapse into stars is modulated by magnetic pressure, which balances gravitational pull, slowing the pace of star formation in some regions, while allowing acceleration in others, producing a dynamic equilibrium that is both flexible and resilient. And this interplay of magnetic force and gravity demonstrates how opposing influences can coexist harmoniously, a principle mirrored in many human and natural systems, where tension and support, action and restraint, operate together to produce stability. And as cosmic rays propagate along field lines, their diffusion is regulated, shaping the radiation environment of entire galactic regions, while simultaneously creating feedback loops that influence gas ionization, chemical reactions, and subsequent star formation, illustrating a continuous, self-regulating system in which subtle forces maintain order over immense scales. And these magnetic effects extend beyond the disk, influencing halo structures and guiding outflows from supernovae and stellar winds, thereby contributing to the galactic ecosystem in a manner that is pervasive yet unobtrusive, reinforcing the principle that some of the most important processes are hidden from immediate perception, yet crucial to the maintenance of structure. And as we visualize the alignment of dust grains along magnetic fields, producing polarized starlight detectable by careful observation, we gain insight into the invisible scaffolding that organizes interstellar space, and this revelation encourages reflection on the unseen forces in our own lives, from emotional support to social networks that stabilize and guide without calling attention to themselves. And as we trace the influence of magnetic fields on gas flows within spiral arms, it becomes evident that even gentle guidance can create large-scale order, allowing millions of stars, nebulae, and molecular clouds to coexist without conflict, following paths defined by collective dynamics rather than individual agency. And this emergent order, born from subtle, pervasive forces, mirrors the natural rhythms of thought and emotion, showing that quiet, consistent principles can sustain complex systems more effectively than abrupt intervention. And as we extend our awareness to include the interplay of galactic rotation, magnetic tension, and turbulent gas motion, a picture of resilient balance emerges, in which energy, matter, and fields are interdependent, each contributing to stability without domination, and the magnetic field's influence on star formation and plasma motion ensures that the Milky Way remains a self-organized, adaptive system, capable of absorbing shocks, redistributing energy, and maintaining coherence over millions and billions of years. And as we imagine these fields extending across light years, subtly guiding cosmic evolution, the mind can perceive a model of patient coordination, where individual motions are regulated, overall patterns are preserved, and even potential chaos is transformed into constructive outcomes. And within star-forming regions, magnetic fields channel jets from young stellar objects, regulate angular momentum, and influence accretion disks, ensuring that stellar birth proceeds neither too quickly nor too slowly, creating a rhythm that is both predictable and adaptive, demonstrating that long-term stability arises from the integration of many small, consistent actions, and this principle resonates with the dynamics of ecosystems, organizations, and neural networks, where the combination of constraint and freedom allows growth, adaptation, and coherence. And as we move outward to the galactic halo and intergalactic medium, magnetic fields, though weaker, continue to shape cosmic structure, guiding plasma filaments, affecting the propagation of cosmic rays, and influencing the distribution of matter on scales that connect galaxies and clusters, illustrating that subtle, invisible forces operate across all scales, linking local behavior to global order. And as we contemplate the pervasive presence of magnetic fields in the universe, we recognize a metaphor for invisible guidance, the quiet scaffolding that stabilizes, supports, and harmonizes processes across space and time. And this recognition encourages reflection on patience, trust, and the efficacy of gentle influence, showing that balance and coherence do not require visibility, noise, or forceful intervention. And as we integrate this understanding with other galactic processes, rotation, density waves, dark matter scaffolding, and stellar dynamics, a holistic vision emerges, where every particle, field line, and energy flow contributes to the galaxy's enduring stability, moving in synchrony yet independently. And this coordinated interplay of forces provides a profound model for observing and managing complex systems, demonstrating that subtle, consistent, and pervasive guidance can maintain harmony across scales, whether in cosmic or human contexts. And as the mind contemplates the invisible threads of magnetism weaving through the Milky Way, a sense of awe, calm, and trust arises, reinforcing the perception that structure, stability, and resilience often emerge from quiet, unobserved forces, and that true coherence does not require immediate recognition or dramatic display, but rather the persistent, patient operation of underlying principles, ultimately revealing that the universe, in its magnetic subtlety, provides both a literal and symbolic blueprint for balance, order, and the gentle orchestration of complexity across time and space, offering a cosmic lesson in patience, harmony, and the quiet power of unseen forces or cosmic rays. High-energy particles traveling near the speed of light traverse the Milky Way and beyond, originating from a variety of sources such as supernova remnants, active star-forming regions, and distant extragalactic events. And although these particles are invisible to the naked eye, their interactions with interstellar gas, magnetic fields, and planetary atmospheres reveal the subtle yet profound ways energy circulates across cosmic distances, carrying information about astrophysical processes and the conditions of space itself. And as we consider their journey, we recognize that cosmic rays diffuse through the galaxy in complex patterns, guided by magnetic fields, deflected by clouds of gas, and slowed by interactions with dust. Yet they never cease in their persistent motion, forming a continuous stream of energy that permeates the galaxy, influencing chemical reactions, ionization levels, and the evolution of molecular clouds. And this ongoing penetration of energy illustrates a principle of connection, that even seemingly distant or isolated phenomena contribute to the broader dynamic of a system. maintaining interaction without the need for direct contact. And as cosmic rays collide with interstellar matter, they generate secondary particles and gamma rays, which in turn illuminate regions of space previously invisible, creating a faint but detectable signature of activity that spreads knowledge about regions light alone cannot reveal. And these processes demonstrate that energy can transmit influence indirectly, without overt disruption, supporting the idea that motion and effect need not be visible to be meaningful. And as we examine the impact of cosmic rays on star-forming clouds, we see that they play a subtle regulatory role, heating the outer layers, affecting ionization, and helping balance the conditions that allow gravity to trigger collapse and eventual stellar birth. And this careful modulation is akin to a natural feedback system, where energy both catalyzes and restrains creation, maintaining a delicate equilibrium across space and time. And when cosmic rays reach planetary atmospheres, such as Earth's, they interact with magnetic fields, the ionosphere, and even biological systems, influencing cloud formation, contributing to radiation exposure, and driving chemical reactions that are part of ongoing cycles essential to climate, atmospheric chemistry, and life itself. And this planetary influence underscores the idea that cosmic scale events are intimately connected with local conditions, demonstrating that distant energies can shape familiar environments in subtle yet critical ways. And as we observe cosmic ray flux over time, patterns emerge that correlate with solar activity, galactic orientation, and supernova frequency, revealing the rhythmic, interconnected nature of the galaxy. And this rhythm offers a model for understanding flow, adaptation, and timing in systems of any scale, from astrophysical to personal or ecological, where energy transfer, feedback, and regulatory processes coexist to maintain stability. And in the interstellar medium, cosmic rays affect magnetohydrodynamic turbulence, propagating energy across scales, accelerating charged particles, and shaping the structure of gas filaments, which in turn influences star formation, chemical enrichment, and galactic evolution. And this cascade of influence illustrates the principle that even small, high-energy constituents can orchestrate large-scale structure over time, through continuous interaction and redistribution of momentum, mass, and energy. And as we extend this awareness to consider the galactic halo, we see that cosmic rays can travel unimpeded for thousands of light years, carrying with them information about ancient events, past supernovae, and the history of energetic processes. And this journey through sparse space serves as a memory of the galaxy's evolution, a persistent trace of action and reaction over immense scales. And their interactions with dark matter, magnetic fields, and diffuse gas provide further insight into the otherwise hidden scaffolding of galactic structure, revealing how even invisible agents contribute to the integrity of the whole. And as we reflect on their subtle yet pervasive presence, cosmic rays become not just carriers of energy, but messengers of the galaxy's ongoing story, threading together regions, events, and processes into a coherent narrative, where each particle's motion integrates into the collective rhythm of galactic activity. And this perspective encourages a contemplative mindset, showing that persistent influence does not require observation or immediate impact, that quiet channels of energy can guide development, stabilize systems, and enable emergence. And as we visualize these particles interacting with clouds, stars, and magnetic fields, we perceive a network of subtle guidance, where energy is distributed, balanced, and redirected to maintain dynamic equilibrium. And this cosmic choreography parallels the flow of information, resources, and influence in complex systems on Earth, whether social, ecological, or neurological, revealing that unseen currents are often the most essential for coherence, resilience, and continuity. And the study of cosmic rays also teaches about thresholds and interactions, showing how high-energy events can trigger secondary processes, without overwhelming the larger system, that extremes can exist alongside calm, and that the universe accommodates both violence and stability simultaneously. and this duality provides insight into coping with stress, intensity, and change in human experience, illustrating that energy can be potent yet constructive when channeled through organized pathways. And as we trace the paths of cosmic rays back to supernovae and other energetic sources, we uncover a web of causality that spans millions of years and thousands of light years, demonstrating that connectivity is both temporal and spatial, and that every local observation is embedded within a vast network of influences, interactions, and histories. And this recognition encourages reflection on patience, perspective, and the value of gradual processes, showing that both creation and understanding unfold over time, guided by persistent, distributed energies. And as cosmic rays continue their ceaseless journey, we see the galaxy as an interconnected organism, where energy, matter, and information flow continuously, maintaining balance, regulating growth, and linking the distant past to the present. And within this vast system, every particle contributes to overall coherence, demonstrating that influence and effect are not confined to visible or immediate domains, and that persistent, subtle guidance often underlies large-scale stability. And this understanding invites a sense of awe, humility, and reassurance, because it shows that even invisible agents, traveling silently across unimaginable distances, sustain order, enable life, and preserve the rhythm of the galaxy, providing a cosmic model for patience, trust, and the power of quiet, enduring influence. And as we meditate on this flow of energetic messengers, we recognize that the universe is both active and calm, violent and harmonious, and that the interplay of these qualities produces the coherent, structured, and resilient system in which we exist, offering a metaphorical and literal template for balance, integration, and the gentle orchestration of complexity, where every action, seen or unseen, contributes to the enduring song of the cosmos. Binary stars, two stars gravitationally bound in a mutual orbit, provide one of the most elegant and intricate examples of cosmic choreography, illustrating how matter, energy, and gravity interact to produce dynamic systems that are simultaneously stable, predictable, and endlessly variable. And as we observe these stellar duets, we see that their motion is dictated not by random chance, but by precise physical laws, with each star influencing the other's orbit, rotation, and even evolution. Yet despite this mutual dependency, the system maintains coherence over millions or billions of years, offering a model for understanding interdependence without chaos. And as the stars orbit their common center of mass, they exchange energy through gravitational tides, stellar winds, and sometimes mass transfer, phenomena that alter luminosity, shape, and surface composition gradually, revealing that even dramatic interactions can be absorbed and moderated by the system, without destabilization. And this gentle modulation of change teaches that interaction and influence do not require abruptness, that motion can be complex yet harmonious, and that connectivity can enhance resilience rather than threaten it. And when binary stars consist of unequal masses, the dynamics become even richer. The larger star exerts a stronger gravitational pull, potentially distorting the smaller companion into an oblate shape, drawing streams of gas in tidal bridges, and occasionally triggering novae or other energetic outbursts. Yet these events occur in patterns that are predictable and bounded by the laws of physics, demonstrating that even extremes are constrained, orchestrated, and integrated into the ongoing rhythm of the system. And as we consider eclipsing binaries, where one star periodically passes in front of the other relative to our line of sight, producing measurable changes in brightness, we appreciate how subtle observation can reveal intricate interactions, how variation can convey information, and how patterns in light serve as a guide to understanding unseen forces and structures. And this concept parallels processes in broader systems, where indirect evidence, regular fluctuations, or rhythmic signals provide insight into underlying dynamics, enabling prediction, analysis, and comprehension without direct interference. And in systems where one component evolves more rapidly, for example, a massive star aging into a red giant, while its companion remains on the main sequence. The transfer of mass, angular momentum, and radiation shapes the evolution of both stars, illustrating that growth and change are relational, dependent on environment and context, and that evolution is rarely solitary, instead being a negotiation between interacting elements. And as we observe contact binaries, where stellar envelopes merge or interact intimately, we witness the remarkable ability of matter to adapt, redistribute, and stabilize even under extreme conditions, forming new structures, maintaining orbital coherence, and sustaining energy balance, demonstrating that even potentially destabilizing forces can be accommodated when regulated by consistent rules. And this insight offers a metaphor for understanding how systems, whether galactic, ecological, or social, can absorb stress, redistribute resources, and continue functioning, emphasizing the importance of structure, feedback, and adaptive balance. And as binary stars orbit, their motion generates detectable phenomena such as Doppler shifts, periodic luminosity changes, and gravitational waves in extreme cases, showing that movement, interaction, and energy emission are inseparable, and that each component's behavior contributes to the measurable signature of the whole system. And this perspective invites reflection on how small, continuous interactions aggregate into observable, meaningful outcomes over time, revealing that patience, observation, and integration are keys to understanding complex dynamics. And when binaries include compact objects like white dwarfs, neutron stars, or black holes, the interactions can be even more energetic. Accretion disks form, jets are emitted, X-ray flares erupt, and yet these processes, while extreme locally, are absorbed into the system's overall behavior, contained by gravity, orbital mechanics, and surrounding matter, illustrating that intensity does not necessarily equate to chaos, that energy can be immense yet organized, and that boundaries, constraints, and context preserve coherence. And in binary systems with relativistic components, gravitational waves ripple outward, carrying energy across vast cosmic distances, providing direct evidence of interaction, motion, and transformation. Yet these waves propagate without disruption to the majority of space, demonstrating that influence can extend far and wide while remaining subtle, controlled, and harmonious. And this teaches that far-reaching effects can coexist with local stability, that force can operate without destructive interference, and that persistence, rhythm, and adherence to principles enable the transmission of impact without instability. And as we observe the formation of binaries from collapsing molecular clouds, we notice that angular momentum, density gradients, and turbulence combine to produce paired stars rather than isolated ones, suggesting that relational structures naturally emerge from conditions and forces, rather than being imposed externally. And this emergence illustrates that patterns, order, and complexity are intrinsic to the laws of physics, and that stability often arises spontaneously through interaction, rather than requiring constant intervention. And in some systems, binaries may evolve into triple or higher order multiple systems, where additional stars introduce further interactions, perturbations, and exchanges of mass and momentum. Yet the system can remain bound, coherent, and predictable, illustrating the adaptability of gravitationally coupled systems, the capacity to absorb new elements, and the resilience of structured motion. And as we expand our view to consider the role of binaries in galactic evolution, we see that they contribute to supernovae, the enrichment of the interstellar medium with heavy elements, X-ray binaries, and gravitational wave sources, subtly influencing the chemistry, dynamics, and energy budget of their host galaxies. And this integrated effect shows that even small-scale interactions, when replicated across millions of systems, can produce galaxy-scale outcomes, reinforcing the principle that micro-level behavior scales naturally into macro-level structure. And as we reflect on these patterns, binaries demonstrate that coexistence, mutual influence, and rhythmic exchange can produce stability, beauty, and long-term coherence, offering a cosmic metaphor for collaboration, interdependence, and the subtle orchestration of forces that maintain harmony without overt control. And finally, the observation of binary stars, their light curves, orbital mechanics, and energetic phenomena invites awe, patience, and contemplation, reminding us that motion, interaction, and influence are continuous, interdependent, and elegantly coordinated, and that the universe, through these cosmic duets, provides a template for understanding balance, adaptation, resilience, and beauty in both physical and conceptual realms, showing that two bodies, through cooperation, exchange, and shared motion, can sustain themselves, shape their environment, and contribute to the grander symphony of the cosmos. An enduring dance that persists across billions of years, whispering lessons about harmony, influence, and the gentle power of interconnectedness, of cosmic jets, the spectacular high-energy streams of plasma ejected from the poles of rotating black holes, neutron stars, or young stellar objects, provide one of the universe's most vivid demonstrations of focused energy, matter, and magnetic fields interacting across scales. And as we observe these jets, we notice that they extend across thousands, sometimes millions, of light years, propagating at near light speeds, yet their motion is guided, coherent, and remarkably structured. A testament to the underlying physical principles that balance gravitational pull, magnetic confinement, and angular momentum. And although jets are incredibly powerful, carrying energy that can rival that of entire galaxies over time, they do not randomly disrupt the cosmic environment. Rather, they carve channels, redistribute matter, and stimulate star formation in surrounding gas clouds, demonstrating that even the most energetic processes can coexist with stability when constrained by consistent laws. And as these jets emerge from accretion disks around compact objects, they reveal the intricate dance between rotation, gravity, and magnetic fields, where twisted field lines funnel charged particles outward, while radiation pressure moderates expansion, creating elongated, luminous structures that serve as both energy conduits and markers of the central engine's activity. And this delicate orchestration exemplifies how intense forces, when channeled properly, produce order rather than chaos, suggesting a universal principle that guidance, boundaries, and interaction can convert raw energy into constructive influence. And when cosmic jets encounter interstellar or intergalactic material, they produce shock fronts, bow waves, and filamentary structures that compress, heat, and sometimes trigger localized star formation, demonstrating that even extreme phenomena can have secondary effects that enrich, create, or regulate, rather than simply destroy. And this interaction emphasizes the interconnectedness of systems, where energy transfer, propagation, and influence ripple outward in ways that shape environments over immense distances and timescales. And as we trace the jets from microquasars within the Milky Way to active galactic nuclei in distant galaxies, we observe similar patterns, revealing a universality in behavior across scales, suggesting that principles governing matter, energy, and magnetism are consistent, whether on stellar or galactic scales. And this universality encourages reflection on how patterns repeat in nature, how complexity can emerge from simple laws, and how predictable structure arises even amidst apparent extremes. And within the jet, particles accelerate through mechanisms such as magnetic reconnection, shock acceleration, and centrifugal forces, producing synchrotron radiation detectable across the electromagnetic spectrum from radio waves to gamma rays. And this radiation, although a byproduct of extreme conditions, provides crucial information about composition, velocity, and magnetic field strength, illustrating that observation can capture both the intensity and subtlety of cosmic processes. And by studying the interaction of jets with their surrounding medium, we gain insight into feedback mechanisms that regulate galactic growth, redistribute energy, and influence cosmic evolution, revealing that high-energy phenomena are not isolated, but integral components of broader cosmic cycles. And as jets precess, wobble, or intermittently flare due to changes in accretion rates, instabilities, or external influences, They demonstrate variability that is both predictable and constrained, showing that even seemingly chaotic behavior is shaped by underlying structure. And this pattern resonates with the understanding that dynamic systems maintain coherence through feedback, regulation, and adherence to natural principles. And when jets terminate, they form lobes, hot spots, or cocoons in the surrounding interstellar or intergalactic medium, regions where energy dissipates, matter accumulates, and new structures emerge. And this gradual dissipation illustrates that energy, no matter how extreme, can integrate with the environment, creating continuity and contributing to stability, emphasizing that influence can be dramatic yet constructive, forceful yet harmonized. And this principle mirrors processes in other cosmic contexts, such as star formation, supernova remnants, or galactic winds, where feedback and interaction foster balance, renewal, and coherence. And as we examine relativistic jets in particular, traveling at significant fractions of light speed, we confront phenomena such as time dilation, Doppler beaming, and apparent superluminal motion, which, while seemingly paradoxical, are perfectly consistent with the laws of physics, revealing that the universe allows for extreme behaviors within constraints that maintain predictability and order. And this teaches that even extraordinary conditions can exist without chaos, that limits, rules, and geometry guide energy and matter towards sustainable paths, and that understanding these constraints transforms awe into comprehension, facilitating both scientific insight and contemplative reflection. And within young stellar jets, often visible in big, haro objects, we observe collimated flows of material ejected from nascent stars interacting with surrounding molecular clouds, producing bright shocks and glowing filaments that illustrate the subtle relationship between nascent stellar activity and environmental shaping, demonstrating that creation, motion, and interaction are inseparable, and that energy flows can simultaneously sculpt and sustain, disturb and nurture. And this duality reinforces the idea that intensity and balance coexist naturally, that force can be constructive, and that systems achieve harmony when energy is channeled thoughtfully, rather than dispersed chaotically, and across cosmic timescales. The persistent activity of jets contributes to the chemical enrichment of galaxies, the redistribution of angular momentum, and the shaping of large-scale structures, showing that localized processes, repeated across numerous instances, drive evolution on grand scales. And this cumulative effect underscores the importance of small-scale interactions in maintaining order, supporting growth, and enabling stability across vast systems. And as we visualize these jets weaving through the darkness of space, illuminated by synchrotron radiation and punctuated by shock fronts, we perceive a rhythm, a directional flow, a cosmic heartbeat that aligns activity, structure, and evolution. And this perception inspires reflection on how guidance, focus, and interaction produce sustained outcomes, how energy and matter interact within boundaries, and how persistence, repetition, and coherence are central to both cosmic and human systems. And ultimately, cosmic jets exemplify the elegance of high-energy astrophysics, where matter, light, and magnetism converge to produce motion that is simultaneously dramatic and controlled, extreme yet integrated, demonstrating that even in the most energetic corners of the universe, structure, rhythm, and balance prevail, offering a profound metaphor for understanding intensity, influence, and the harmonious orchestration of forces across space and time. And as we contemplate the cascading flows of plasma, magnetic fields, and radiation, we recognize that the cosmos operates through subtle guidance, persistent rhythm, and interconnected motion, a template for comprehension, reflection, and awe. And through this awareness, cosmic jets become not only phenomena of physics, but instruments of meditation, symbols of dynamic harmony, and reminders that even the most extreme energy, when constrained, channeled, and integrated, contributes to enduring order, coherence, and beauty across the universe. A breathtaking dance that extends from the heart of black holes to the farthest reaches of galaxies, and that continues to shape, illuminate, and inspire across billions of years, offering lessons about patience, influence, and the gentle power of focused motion. Supernovae, the cataclysmic explosions marking the violent death of massive stars, or the sudden thermonuclear ignition of white dwarfs in binary systems, are among the most energetic, transformative, and visually spectacular events in the cosmos, releasing in a matter of days or weeks as much energy as our sun emits over its entire 10 billion year lifetime. And as we observe these explosions across the electromagnetic spectrum, from gamma rays and X-rays to visible light and radio waves, we gain insight into fundamental physics, nucleosynthesis, and the dynamic processes that sculpt galaxies, enrich the interstellar medium, and influence subsequent generations of star formation, because the expelled material, traveling at thousands of kilometers per second, distributes heavy elements like iron, calcium, oxygen, and carbon into surrounding space, seeding future stars, planets, and potentially life. And this dispersal demonstrates the cyclical nature of matter in the universe, where endings are intimately linked to creation, and where energy, mass, and influence propagate across vast distances and timescales, shaping structures and processes far beyond the immediate vicinity of the explosion. And as we study the mechanics behind supernovae, we observe the interplay of core collapse, neutrino emission, shock waves, magnetic fields, and rotational dynamics, each contributing to the complex morphology, light curve, and remnant formation that follows. And this intricate orchestration illustrates the precision and predictability embedded within what at first appears chaotic, showing that even extreme, high-energy phenomena obey universal physical laws, and that their seemingly unpredictable appearance is the product of deep underlying structure, governed by initial stellar mass, composition, rotation, and environment. And as supernova remnants expand into space, they create shock fronts that compress surrounding gas, trigger star formation, and redistribute energy, momentum, and chemical elements, forming vast nebulae that may persist for tens of thousands of years. And this feedback mechanism highlights the interconnectedness of cosmic systems, demonstrating how a single event can influence regions spanning hundreds of light years, with implications for galaxy evolution, star cluster dynamics, and planetary system formation. And the visible remnants, such as the Crab Nebula, Cassiopeia A, and Tycho's supernova remnant, offer a laboratory for studying high-energy physics, particle acceleration, magnetic field amplification, and radiation mechanisms, providing a multi-layered understanding of processes that operate across scales and link the microphysics of particles with the macroscopic structure of galaxies. And as we trace the evolution of supernovae, from progenitor instability to core collapse or thermonuclear runaway, shock breakout, peak luminosity, and gradual fading into remnant, we see a narrative of transformation that mirrors principles of energy conservation, momentum transfer, and structural reorganization, showing that even violent events can produce coherent outcomes that sustain and enrich larger systems. And within these explosions, neutrinos play a crucial yet subtle role, carrying away energy, driving shock revival, and offering insight into weak nuclear interactions and fundamental particle physics, demonstrating that some of the most influential processes are invisible, operating quietly yet decisively, a principle echoed throughout cosmic systems, where unseen forces like dark matter, magnetic fields, or radiation pressure guide the evolution and stability of structures without dramatic visibility. And as astronomers capture light curves, spectra, and multi-wavelength images of supernovae, they can reconstruct progenitor properties, explosion dynamics, and chemical yields, revealing patterns that inform models of stellar evolution, galactic chemical enrichment, and the origin of elements essential for life. And this deep connection between observation, theory, and modeling highlights how knowledge emerges from persistent study, careful inference, and the integration of multiple data streams, mirroring the layered processes by which the universe itself evolves, where cumulative effects, slow feedback, and long-term interactions produce order, diversity, and resilience. And as we consider the sheer scale of energy released, with peak luminosities sometimes outshining entire galaxies, we are reminded of the vast power inherent in stellar evolution. Yet this power, though immense, is integrated into the cosmic system without destabilizing it, because gravity, mass distribution, and interstellar interactions regulate the effects, distributing energy and matter in ways that promote balance and continuity. And this principle, that extreme forces can exist within a structured, self-regulating system, provides a profound lesson about stability, resilience, and the harmonization of intensity with order, a lesson applicable from galaxies to individual awareness, and the diversity of supernova types, including Type A, Type ABC, and Type II, each governed by different progenitor conditions, nuclear processes, and binary interactions, illustrates how variation emerges within universal constraints, showing that the universe can produce rich diversity while maintaining predictable physical laws. And this balance between variety and order reinforces the notion that structure and creativity coexist seamlessly, both in cosmic evolution and potentially in human understanding. And as we observe the remnants, filaments, knots, and expanding shells, shaped by hydrodynamic instabilities, magnetic tension, and radiative cooling, we see the interplay of chaos and coherence, turbulence and symmetry, demonstrating that complex, beautiful structures arise naturally from interactions between energy, matter, and environment, and that apparent disorder is often a manifestation of deeper organization and regularity, a perspective that can inform both scientific inquiry and philosophical reflection. And the temporal aspect of supernovae, with rapid explosive phases followed by slow remnant evolution, teaches patience and perspective, as we recognize that change and transformation occur on multiple scales, from instantaneous to millennial, and that understanding requires attention, integration, and long-term observation. And as light from supernovae travels across the galaxy and beyond, it illuminates cosmic distances, probes interstellar dust, and enables measurement of fundamental constants, expansion rates, and cosmic distances, showing that even transient events can have enduring influence, shaping perception, measurement, and comprehension on a universal scale. And as we imagine the effect of these explosions on nearby systems, we see the duality of creation and destruction, where energy and matter simultaneously annihilate and nurture, destroy and seed, demonstrating that endings are not absolute but transformative, and that influence persists, propagates, and inspires formation of new structures. And within this understanding, supernova become not merely destructive, but deeply generative phenomena, embodying the balance of intensity, consequence, and sustainability, offering insight into the rhythms of the universe, the continuity of matter, and the interplay between force and structure. And ultimately, these explosive engines of the cosmos illuminate not only the heavens, but also fundamental principles of persistence, balance, interconnectedness, and transformation, guiding scientific exploration, philosophical reflection, and even meditative contemplation, because through observing, modeling, and reflecting on supernovae, we perceive the universe as a network of energy, matter, and influence, where endings catalyze beginnings, extreme forces coexist with stability, and the interplay of destruction and creation maintains the enduring, dynamic harmony of cosmic evolution, providing both knowledge and profound inspiration for anyone seeking to understand the rhythm, power, and beauty of the universe. Black holes, those enigmatic regions of spacetime, where gravity becomes so intense that not even light can escape, represent the extreme limits of physical law, yet their presence, influence, and interactions with their surroundings provide profound insight into the structure, dynamics, and evolution of the universe. Because despite being invisible in the conventional sense, they exert measurable effects on stars, gas, dust, and even entire galaxies, shaping motion, feeding growth, and catalyzing energetic phenomena that ripple across vast cosmic distances. And as we observe accretion disks spiraling toward event horizons, heated to millions of degrees by friction, turbulence, and relativistic effects. Emitting X-rays and gamma rays that traverse interstellar space, we gain understanding of fundamental physics under conditions unattainable in laboratories on Earth, testing our understanding of general relativity, quantum mechanics, and high-energy particle interactions, and the jets produced by some supermassive black holes, propelled along rotational axes at near light speeds, illuminate surrounding material, regulate star formation, and redistribute energy and momentum over hundreds of thousands of light years, demonstrating that even objects defined by invisibility can dominate the structure and evolution of galaxies through subtle, sustained influence. And as stellar, mass black holes interact with companion stars in binaries, siphoning matter through gravitational attraction, forming X-ray binaries, or emitting gravitational waves during inspiral and merger, we witness the duality of destruction and creation, where energy, mass, and angular momentum are transformed, redistributed, and radiated, influencing systems far beyond their immediate vicinity. And these processes allow us to trace the life cycles of massive stars, the formation of neutron stars and black holes, and the assembly of complex gravitational hierarchies, showing that black holes, while often perceived as endpoints or voids, are deeply generative, shaping cosmic evolution, chemical enrichment, and energy distribution. And as we consider supermassive black holes anchoring galactic centers, such as Sagittarius A in the Milky Way, we see the role of central mass concentrations in regulating stellar orbits, spiral arm structure, and nuclear star formation, demonstrating that even in their invisibility, these objects provide stability, orientation, and reference frames within galaxies, and their gravitational influence extends across thousands of light years, sculpting galactic morphology, regulating inflow and outflow of gas, and maintaining equilibrium amidst vast dynamical interactions. And the study of black hole mergers through gravitational wave astronomy, pioneered by LIGO and Virgo, reveals the subtle, rippling effects of spacetime distortions, carrying information about mass, spin, orientation, and cosmic distance, enabling us to probe regions previously inaccessible, and to witness the dance of massive objects across billions of years in light years, while also testing the limits of general relativity, the nature of compact objects, and the interactions of extreme matter and energy. And as theoretical models explore the interior, singularity, and event horizon structure, along with Hawking radiation, quantum tunneling, and information paradoxes, we confront profound questions about the nature of reality, causality, and the limits of knowledge, recognizing that black holes challenge our understanding not by absence, but by extreme presence, where conventional intuition fails, and rigorous mathematical frameworks are essential. And as matter approaches these objects, tidal forces stretch, compress, and heat material, producing phenomena such as spaghettification, relativistic jets, and luminous flares, demonstrating the intimate interplay between gravity, motion, and energy. And these processes, while violent locally, contribute to the galaxy's long-term stability and evolution by redistributing matter, energy, and angular momentum. And as we map the surrounding environment of supermassive black holes, we observe circumnuclear disks, toroidal dust structures, and star clusters that are influenced, yet not destroyed, by the intense gravitational field, illustrating that even the most extreme forces operate within predictable boundaries, regulating, shaping, and sustaining larger structures. And as we consider intermediate, mass black holes, potentially bridging the gap between stellar remnants and galactic nuclei, we explore pathways of hierarchical assembly, cluster dynamics, and the growth of cosmic structures, showing that black holes participate in multiscale interactions, from local binary systems to galaxy-wide evolution. And as gravitational lensing reveals the warping of spacetime around these objects, magnifying and distorting distant light, we gain both observational leverage and a profound visual metaphor for the bending, shaping, and interconnection of the cosmos, where even invisible objects leave an indelible mark, influencing perception, measurement, and understanding across immense distances, and as we reflect on black holes' role in cosmology, including their potential contribution to reionization, feedback processes, and cosmic evolution, we recognize that these entities, defined by extreme density, curvature, and energetic processes, exemplify how the universe organizes, regulates, and sustains complexity through subtle yet decisive influence. And this principle extends from the microscopic quantum realm, where black hole thermodynamics, Hawking radiation, and information conservation challenge our comprehension, to macroscopic structures like galaxies, clusters, and filaments, revealing continuity, coherence, and integration across scales, and the formation pathways of black holes, whether from core, collapse supernovae, accretion-induced collapse, or direct collapse in early protogalaxies, demonstrate the universality of gravitational physics, the interplay between mass, angular momentum, and energy, and the emergent properties of self-organizing systems, showing that even in seeming chaos or destruction, order, structure, and predictable outcomes arise naturally, and the role of black holes in feedback mechanisms, from quenching star formation to powering active galactic nuclei, highlights the principle that extreme objects regulate, rather than destabilize, complex systems, guiding evolution through subtle, persistent influence, a principle echoed in nature at all scales, from planetary systems to ecological networks, and as we explore relativistic effects near event horizons, including time dilation, frame dragging, and gravitational redshift, we confront a universe where observation, experience, and measurement are intrinsically linked to the geometry of spacetime, reminding us that perception, causality, and influence are not absolute, but context-dependent, and that the most extreme entities test the boundaries of both experience and theory, driving innovation, discovery, and conceptual expansion. And as we map black hole populations across the cosmos, measure their spins, masses, and merger rates, and model their interaction with dark matter, gas, and stars, we see an intricate web of cause, effect, and feedback, demonstrating that even isolated, invisible entities participate in the continuous shaping, structuring, and guiding of the universe, where every mass, motion, and energy transfer contributes to the unfolding of cosmic evolution, and this understanding encourages reflection on the principles of balance, persistence, and subtle influence, as black holes exemplify the notion that power, intensity, or invisibility need not disrupt, but can organize, regulate, and sustain systems, providing a model for thinking about dynamics, interaction, and resilience at every scale, from human cognition to galactic evolution. And ultimately, black holes are not simply voids or endpoints, but dynamic sculptors, architects, and regulators, whose gravitational mastery shapes the structure, motion, and energy distribution of the cosmos, offering both scientific insight and profound philosophical perspective, reminding us that even in the most extreme, invisible, or inaccessible regions of existence, influence, order, and interconnectedness prevail, guiding the rhythm, evolution, and harmony of the universe across space and time. Neutron stars, the ultra-dense remnants of massive stars that have exhausted their nuclear fuel and undergone supernova collapse, represent some of the most extreme physical conditions in the universe, where matter is compressed to densities exceeding that of atomic nuclei, creating environments in which quantum mechanics, relativity, and nuclear physics converge in ways that challenge our understanding and offer unparalleled opportunities for studying fundamental forces. Because within these stars, a teaspoon of matter would weigh billions of tons on Earth, illustrating the staggering concentration of mass and the dramatic effects of gravity at small scales. And as we observe pulsars, rotating neutron stars emitting beams of electromagnetic radiation, we witness precise cosmic clocks whose rotational periods, often measured in milliseconds to seconds, reveal information about the internal structure, magnetic field strength, and evolution of the star, providing insight into the interplay between angular momentum, magnetic fields, and radiation. And these pulsars, by their regularity, enable tests of general relativity, including frame, dragging and gravitational wave propagation, especially when found in binary systems where the interaction with companion stars produces orbital decay, spin changes, and relativistic timing variations, demonstrating the interconnectedness of extreme matter, space-time geometry, and cosmic evolution. And as we consider magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, we are confronted with environments where magnetic pressure dominates, crustal stresses produce starquakes, and bursts of X-ray and gamma-ray emission illuminate the surrounding space, revealing how fundamental forces interact at levels inaccessible in terrestrial laboratories. And these bursts, while brief, can temporarily outshine entire galaxies in high-energy radiation, illustrating the potential of neutron stars to influence their environment dramatically despite their small size. And as neutron stars accrete matter from binary companions, forming X-ray binaries, they provide laboratories for studying thermonuclear bursts, angular momentum transfer, and disk magnetosphere interactions, revealing how matter behaves under extreme gravity, rapid rotation, and intense magnetic fields. And these processes help us understand nucleosynthesis, the limits of neutron degeneracy pressure, and the conditions under which collapse to a black hole occurs, connecting microphysical processes to macroscopic outcomes. And the equation of state of neutron star matter, describing the relationship between pressure, density, and temperature, remains one of the most profound open questions in physics, because it ties directly to the behavior of strong force interactions, superfluidity, superconductivity, and exotic particles like hyperons or quark matter, suggesting that neutron stars are cosmic laboratories where the fundamental building blocks of matter reveal themselves under extraordinary conditions. And as gravitational wave detectors, such as LIGO and Virgo, observe neutron star mergers, we gain unprecedented access to the dynamics of ultra-dense matter, relativistic orbital decay, and the production of heavy elements like gold and platinum through rapid neutron capture processes, demonstrating that these compact stars are not isolated curiosities, but essential contributors to the chemical evolution of the universe, enriching galaxies with elements critical for planet formation and life. And as these mergers produce kilonovae, emitting across the electromagnetic spectrum, they allow multi-messenger astronomy to probe connections between gravitational waves, gamma-ray bursts, and nucleosynthesis, showing how neutron stars integrate multiple forms of cosmic influence into a coherent, observable narrative. And as we consider the rotational and thermal evolution of neutron stars over millions of years, including spin down due to magnetic braking and cooling through neutrino emission, we observe that even in extreme conditions, matter follows predictable, structured processes, offering models for understanding energy transfer, angular momentum conservation, and long-term stability under forces that far exceed human experience. And the crust of a neutron star, composed of nuclei embedded in a neutron-rich lattice, supports the study of nuclear pasta phases, superfluid vortices, and crust-core interactions, illustrating that matter under extreme pressure and density can organize into exotic, ordered structures with mechanical, thermal, and magnetic properties that influence observable phenomena such as glitches, thermal X-ray emission, and magnetospheric activity. And as we study pulsar timing arrays, searching for correlations in rotational irregularities, we detect subtle perturbations that encode information about gravitational waves, from supermassive black hole binaries and cosmological structure, highlighting that neutron stars, despite their compactness, act as sensitive probes of spacetime on the largest scales, connecting the very small to the very large. And as we analyze high-energy emissions, magnetospheric currents, and particle acceleration in neutron star environments, we find parallels to plasma physics, magnetohydrodynamics, and particle interactions under extreme field strengths, revealing that these stars embody a natural laboratory, where theoretical models can be confronted with precise, multi-wavelength observations. and this synthesis of theory and observation underscores the utility of neutron stars as keystones in astrophysics, bridging stellar evolution, nuclear physics, and cosmology, while inspiring questions about the ultimate limits of matter, gravity, and energy. And as we consider the distribution of neutron stars in galaxies, including isolated pulsars, binary systems, and remnants in globular clusters, we see that these objects, though small and dense, influence galactic dynamics, stellar populations, and interstellar medium conditions, contributing to the long-term structural and energetic balance of their host systems, and the study of their birth and core collapse supernovae informs our understanding of progenitor mass thresholds, explosion mechanisms, neutrino physics, and shock propagation, connecting the life cycle of massive stars to the creation of compact objects, while providing constraints on the frequency, distribution, and characteristics of neutron stars across cosmic time. And as we model neutron star interiors, considering superfluid neutron vortices, proton superconductivity, and crustal elasticity, we gain insight into rotational evolution, glitch phenomena, thermal transport, and magnetic field decay, revealing that even under extreme compression and density, matter exhibits organized behavior, responding to forces in predictable ways that can be quantified, predicted, and observed. And as we explore the potential for exotic states of matter, such as deconfined quarks, hyperons, or Bose-Einstein condensates in cores, neutron stars challenge the boundary between known physics and theoretical extrapolation, illustrating that the universe provides natural experiments beyond any laboratory, where theory meets observation under conditions unimaginable on Earth, and the interactions of neutron stars with surrounding supernova remnants, pulsar wind nebulae, and interstellar medium provide insights into feedback mechanisms, energy deposition, and magnetohydrodynamic interactions, showing that these compact objects, though small in size, exert influence over vast spatial scales, regulating local environments and contributing to galactic ecology. And as observational techniques improve, including X-ray timing, radio interferometry, and gravitational wave detection, we refine models of internal composition, magnetic field geometry, and emission mechanisms, confirming that neutron stars serve as touchstones for high-energy astrophysics, fundamental physics, and multi-messenger astronomy, bridging scales, phenomena, and disciplines. And ultimately, neutron stars embody a synthesis of extremity and structure, revealing how matter, energy, and space-time interact under the most intense conditions, providing a continuous source of insight, inspiration, and exploration, as these cosmic laboratories demonstrate that even under forces, densities, and energies far beyond human experience, patterns, stability, and predictable behavior emerge, guiding our understanding of the universe, from the microscopic to the cosmic, and offering a profound model for the interplay of chaos, order, and continuous, elegant evolution. The universe is a vast, dynamic tapestry of light, color, and energy, and the science of color in the cosmos reveals not only the intrinsic properties of matter, but also the processes, interactions, and physical laws that govern every observable phenomenon, because color, in an astronomical context, is fundamentally tied to the wavelength of electromagnetic radiation emitted, absorbed, or reflected by celestial objects, and as we examine stars, their color directly corresponds to surface temperature, with hotter stars radiating blue or white light and cooler stars emitting red or orange hues, and this basic stellar classification, understood through blackbody radiation and the Planck distribution, provides insights into stellar mass, age, and life cycle, allowing astronomers to infer how stars evolve from their birth in dense molecular clouds to their ultimate fates as white dwarfs, neutron stars, or black holes, while simultaneously shaping the visual panorama of the night sky in a spectrum of hues that, although often imperceptible to the human eye in deep space, encode vast amounts of physical information. And beyond individual stars, galaxies exhibit characteristic colors, resulting from the composite light of billions of stars, interstellar dust, and gas with young star forming regions emitting strongly in ultraviolet and blue, while older, quiescent galaxies glow in redder wavelengths. And this interplay of light allows astrophysicists to reconstruct the history of star formation, chemical enrichment, and galactic evolution across cosmic time, providing a window into the past, present, and future of the universe. And as we consider nebulae, these clouds of gas and dust display spectacular colorations due to emission lines, reflection, and absorption processes, where hydrogen, oxygen, and sulfur, for instance, emit at characteristic wavelengths when ionized by nearby stars, producing vivid reds, greens, and blues that are not only visually striking but physically diagnostic, revealing the temperature, density, chemical composition, and ionization states of interstellar matter. And these glowing clouds, in turn, trace the locations of active star formation, shock fronts from supernovae, and interactions between stellar winds and the surrounding medium, providing astronomers with a living map of the dynamic processes shaping the interstellar environment, while offering an aesthetic bridge between human perception and cosmic physics. And as we examine the light from distant galaxies and quasars, redshift due to the expansion of the universe alters the observed color, stretching light toward longer wavelengths, and revealing not only the velocity and distance of these objects, but also the history of cosmic expansion, the behavior of dark energy, and the large-scale structure of the universe, connecting color to fundamental cosmological parameters, and offering a quantitative tool to probe the very fabric of spacetime. And the presence of dust, both in galaxies and the intergalactic medium, modifies the apparent color of light by scattering and absorption, a process that astronomers must correct to recover intrinsic spectra, while simultaneously providing insights into the composition, distribution, and evolution of cosmic dust, which plays a key role in cooling gas clouds, forming planetary systems, and seeding the universe with the ingredients for life, demonstrating that the study of color extends beyond mere observation, becoming a crucial diagnostic of physical, chemical, and evolutionary processes. And as we consider high-energy phenomena, such as supernova remnants, active galactic nuclei, and gamma-ray bursts, color and spectral energy distribution encode information about extreme temperatures, particle acceleration, magnetic fields, and relativistic effects, revealing the mechanisms by which energy is generated, transported, and radiated across scales from subatomic to intergalactic. And these high-energy signatures, often invisible to human eyes but detectable in X-ray, ultraviolet, or infrared regimes, underscore the fact that the universe glows across the electromagnetic spectrum, with each wavelength providing unique insight into physical conditions, energetic events, and the life cycle of matter. And as instrumentation and observational techniques have advanced, from ground-based telescopes with CCD detectors to space-based observatories spanning radio to gamma rays, astronomers have been able to reconstruct full, color images, spectral maps, and time-resolved observations that reveal the structure, motion, and interaction of cosmic matter with unprecedented clarity, demonstrating that color is not merely aesthetic, but the universe is a vast chemical laboratory, where elements forged in the hearts of stars, in the explosions of supernovae, and within the primordial nucleosynthesis of the Big Bang combine to create the rich tapestry of matter and color that we observe. And understanding cosmic chemistry allows us to trace the origins, distribution, and evolution of every atom in existence, because the type, abundance, and interaction of elements dictate not only the physical behavior of matter, but also the light it emits, absorbs, or scatters, thereby shaping the colors and spectra observed across the cosmos. And as we examine stellar interiors, hydrogen fusion into helium through the proton chain, or the CNO cycle, produces energy that ultimately manifests as visible light, ultraviolet, and infrared radiation, the specific wavelengths of which are determined by the elements present, their ionization states, and the temperatures and pressures within stellar cores. And this fusion process continues to build heavier elements like carbon, oxygen, neon, and iron through successive stages in massive stars, with each newly formed element influencing opacity, energy transport, and spectral output, thereby leaving identifiable signatures that astronomers can detect through spectroscopy. And when these massive stars reach the end of their lives, explosive supernovae disperse these elements into surrounding space, seeding molecular clouds with the raw material for new stars, planets, and ultimately, life, while the shock waves generated by these explosions compress gas and dust, triggering further star formation and creating glowing remnants whose emission lines and spectral colors reflect the chemical composition of the ejected material, providing a direct link between elemental synthesis and cosmic light. And beyond stars, interstellar and circumstellar environments contain complex molecules, ions, and dust grains, including carbon chains, silicates, and polycyclic aromatic hydrocarbons, which absorb and re-emit light in specific bands, producing color variations that map the chemical richness of nebulae, protostellar regions, and planetary disks. And these processes not only influence the aesthetics of the night sky, but also determine the thermal balance, chemistry, and opacity of the interstellar medium, with subtle differences in elemental abundance, leading to measurable variations in spectral features, line strengths, and photometric colors, enabling astronomers to reconstruct the chemical evolution of galaxies over billions of years, from the first generation of metal, poor population Ethereal stars to the diverse chemical compositions seen in modern galaxies. And as we extend our observations to extragalactic scales, the distribution of elements, as inferred from emission and absorption lines in galaxies, clusters, and the intergalactic medium, reveals patterns of enrichment, gas inflow and outflow, star formation histories, and interactions, demonstrating that cosmic chemistry drives not only color, but also the large-scale dynamics, structure, and evolution of the universe. And the presence of trace elements, isotopic ratios, and molecular complexes provides clues to nucleosynthetic pathways, mixing processes, and the influence of phenomena like cosmic rays, stellar winds, and black hole activity, with each spectral signature acting as a chemical fingerprint, allowing astronomers to piece together the life cycle of matter, from the Big Bang to present-day cosmic structures. And as we examine planetary atmospheres, the absorption and scattering of light by molecules such as oxygen, nitrogen, water vapor, carbon dioxide, and methane produces the distinct colors of planetary disks, sunsets, and aurorae, illustrating that cosmic chemistry manifests not only in distant stars and galaxies, but also in the local, tangible universe of planets, moons, and rings. And this chemical interplay drives climate, habitability, and surface coloration, providing a bridge between astrophysics, planetary science, and the human experience of observing color. And in addition to emission and absorption, the interaction of light with dust grains, whether carbonaceous, silicate, or ice-coated, creates scattering effects, polarization, and reddening that further influence perceived color, revealing the size distribution, composition, and spatial distribution of interstellar and circumstellar dust. And these observations in turn inform models of star and planet formation, grain growth, and the evolution of protoplanetary disks, demonstrating that chemistry is deeply intertwined with both color and structure. And as astronomers use spectroscopy, photometry, and imaging across multiple wavelengths, from radio to X-ray, they can decode the chemical fingerprints embedded in light, reconstructing temperature, density, elemental ratios, and molecular abundances, while revealing dynamic processes such as shock heating, photoionization, and molecular cooling, all of which contribute to the observable colors of nebulae, star-forming regions, and galaxies, and the presence of exotic elements, short-lived isotopes, and complex organics in space, sometimes detected in meteorites, comets, or interstellar clouds, provides insights into nucleosynthesis, the recycling of matter, and the conditions for prebiotic chemistry, showing that the universe's palette is not only beautiful, but fundamentally tied to the very processes that enable life. and this awareness enriches both scientific understanding and aesthetic appreciation, because it demonstrates that every photon carries information about the chemical history, physical conditions, and evolutionary pathways of the matter that emitted it. And as we map the chemical composition of the Milky Way and other galaxies, we see gradients, clusters, and pockets of enrichment that reflect the interplay between star formation, feedback, galactic dynamics, and cosmic accretion, illustrating that chemical diversity drives both structure and appearance, and that color is a tangible manifestation of elemental abundance and interaction. And by connecting the physics of atomic and molecular transitions to the astrophysical processes that govern the cosmos, we recognize that every shade, hue, and glow in the universe is a signature of chemical activity, whether in the faint wisps of an emission nebula, the brilliant blaze of a supernova, or the subtle redshift of distant galaxies. And this understanding allows humanity to read the universe's chemical story through its colors, linking observation to theory, light to matter, and beauty to science. And ultimately, the study of cosmic chemistry reveals that the colors of the universe are not mere decoration, but the direct, measurable consequence of atomic and molecular processes, stellar evolution, and galactic dynamics, providing a continuous, intricate, and harmonious portrait of creation, transformation, and cosmic interconnectedness. A universe in which every element, every photon, and every hue contributes to the grand, glowing tapestry of existence, demonstrating that color is both a messenger and a map, encoding the fundamental laws, history, and ongoing evolution of the cosmos across unimaginable scales of space and time. And through this lens, we perceive the universe not only as visually stunning, but as a vast chemical network, constantly active, constantly evolving, where matter and energy interact to produce both structure and the sublime, illuminating the cosmic dance of atoms and light, connecting the smallest quantum processes to the largest galactic structures, revealing a universe that glows not randomly, but with purpose, physics, and story, a universe in which every color tells of origin, transformation, and the enduring flow of creation itself. The universe presents itself not merely as a collection of luminous objects scattered through empty space, but as a complex interplay of light and shadow, a dynamic theater in which radiation interacts with matter across scales from subatomic particles to galactic superstructures. And this interaction fundamentally shapes how we perceive the cosmos, influencing everything from the glow of nebulae to the dark silhouettes of dust lanes, the deep shadows cast by planets, and the subtle contrasts between stellar clusters. And as photons traverse the interstellar medium, they are absorbed, scattered, refracted, and emitted by atoms, ions, and dust grains, creating gradients of brightness, spectral lines, and diffuse halos that encode the physical and chemical conditions of the medium. And this delicate balance between illumination and obscuration allows astronomers to reconstruct three-dimensional structures from two-dimensional images, infer the presence of hidden matter such as dark clouds or planetary disks, and identify processes that are otherwise invisible, like star formation, shock fronts, or radiative cooling, while also conveying the emotional and aesthetic impact of the cosmos, because the dance of light and shadow produces depth, texture, and contrast that resonate with human perception and imagination, creating the familiar sense of awe that comes from observing a Milky Way stretching across the night sky, a supernova remnant glowing against a dark nebular backdrop, or the subtle glimmer of distant galaxies faintly illuminated across billions of light years. And within this interplay, the orientation, density, and composition of interstellar and circumstellar material determine whether light penetrates freely or is blocked and diffused, producing color variations, silhouette effects, and reflection nebulae that highlight structure while softening direct glare, enabling a gentle visual rhythm that can be interpreted scientifically yet experienced aesthetically. And as light passes through molecular clouds, ultraviolet photons from young stars ionize gas, producing emission lines in red, green, and blue that depend on the specific elements present and their excitation states, while simultaneously being absorbed by dust grains that radiate in infrared wavelengths, creating a multi-layered spectrum in which each wavelength offers a different window into the underlying physics, chemistry, and dynamics. And these processes are further complicated by magnetic fields, turbulence, and stellar winds, which alter density distributions, channel gas flows, and create filamentary structures that cast long shadows, scatter light unevenly, and produce asymmetric features, thereby revealing the interaction between energy input, material properties, and gravity in shaping observable patterns. And in the context of planetary systems, light and shadow dictate not only color and visibility, but also perception of topography, seasonal variations, and atmospheric phenomena, as sunlight glances across craters, mountains, ice caps, and clouds, highlighting relief, creating gradients, and enabling the study of albedo, reflectivity, and composition. With these subtle cues providing critical insight into geological processes, climate, and potential habitability, while at the larger scale of galaxies, the interplay of luminous stars and obscuring dust lanes produces the iconic spiral patterns, bars, and rings observed in the Milky Way and other systems, where concentrated clusters of bright stars punctuate darker regions, revealing density waves, star formation fronts, and regions of active feedback. And this structure is mirrored across wavelengths, as optical images reveal visible starlight, infrared maps reveal dust and cool stars, ultraviolet captures hot young populations, and radio wavelengths trace neutral hydrogen and molecular gas, each highlighting different aspects of the light and shadow dynamic. And in galaxy clusters, the combination of intracluster gas emitting X-rays and gravitational lensing producing distorted images of background galaxies further illustrates that light can be bent, amplified, and shadowed by the invisible scaffolding of dark matter, integrating the seen and unseen into a coherent observational framework that reflects both matter distribution and cosmic evolution. And these complex interactions emphasize that perception of the universe is fundamentally relational, dependent not only on intrinsic luminosity, but also on the environment, orientation, and intervening material, such that brightness, color, and contrast are emergent properties of the interplay between source, medium, and observer. And as astronomers model these interactions, they develop sophisticated radiative transfer codes, three-dimensional simulations, and multi-wavelength surveys that reveal hidden populations, track evolution, and predict observational signatures of phenomena that would otherwise remain invisible, while simultaneously demonstrating that the visual beauty of the cosmos arises from the same physics that governs its structure and evolution, illustrating that aesthetic experience and scientific understanding are inseparable when considering light and shadow. And on a more philosophical level, the interaction of illumination and obscuration mirrors human perception and cognition, highlighting how visibility and awareness are mediated by context, medium, and perspective, suggesting that what is observed is never independent of the environment, and that unseen structures can have profound influence, guiding motion, stability, and growth even without direct perception. And just as photons are absorbed, scattered, and redirected, so too are knowledge, influence, and energy in the universe filtered, moderated, and distributed, demonstrating that subtle guidance often underlies apparent simplicity. And as we consider high-energy phenomena, such as supernovae, active galactic nuclei, or gamma-ray bursts, the interplay of light and shadow becomes more extreme, with dense ejecta, accretion disks, and relativistic jets casting shadows, shaping emission regions, and producing spectral features that inform the underlying mechanics, energy transport, and elemental composition, while also contributing to the overall visual signature of these events, integrating sudden intensity with surrounding calm, in a way that preserves coherence while highlighting contrast. And within star-forming regions, the balance of illumination from massive stars against the dark molecular clouds creates iconic pillars, filaments, and globules, where shadows define shape, channel flows, and modulate feedback, providing natural laboratories for studying radiative influence, gas dynamics, and the emergence of protostars, while simultaneously evoking a profound sense of scale, depth, and tranquility, because the eye and mind can follow light and shadow along paths that reveal both order and complexity. And as we extend these considerations across cosmic time, we see that the interplay of light and shadow is not static, but evolves as stars form, die, and migrate, as gas is compressed and expelled, and as galaxies interact, merge, and accrete, such that color, brightness, and contrast encode history, dynamics, and chemical evolution, offering a multi-dimensional record accessible through careful observation, spectroscopy, and modeling, and ultimately, understanding the interplay of light and shadow allows us to interpret the universe, not merely as points of brightness, but as an interconnected system in which illumination, obscuration, emission, and absorption act together to produce the visual, physical, and emotional richness we observe, providing a framework in which both aesthetic appreciation and scientific inquiry are informed by the same fundamental principles, linking quantum processes, atomic physics, and radiative interactions to the vast structures of galaxies, clusters, and cosmic filaments, while demonstrating that perception is inherently relational, context-dependent, and emergent, and that the universe's beauty, coherence, and color are direct consequences of the continuous, delicate, and dynamic dance between light and shadow, a dance that encodes matter, energy, history, and law, allowing every photon, every dark lane, every glow, and every silhouette to contribute to a cosmic narrative that is both scientifically decipherable and profoundly moving, a universe where light reveals, shadow informs, and perception integrates, creating a holistic, living portrait of cosmic order, motion, and color across space and time. And by recognizing this interplay, humanity gains not only a deeper understanding of astrophysics, but also a richer experience of the sublime, a sense of connection to processes unfolding across billions of years, where every illuminated path and every gentle shadow contributes to the coherent, enduring, and radiant tapestry of existence, inviting both contemplation and exploration, observation and meditation, in which the mind can follow the rhythms of light and shadow across nebulae, star clusters, planetary systems, and galaxies, tracing an endless, harmonious, and patient choreography that defines the visual, chemical, and structural essence of the universe. Every star, from the tiniest red dwarf to the most massive blue supergiant, emits light that carries a fingerprint of its physical state, a spectrum that encodes temperature, chemical composition, pressure, magnetic fields, and motion. And by dispersing this starlight through prisms or diffraction gratings, astronomers can decode the hidden information contained within, revealing not only the elements present, hydrogen, helium, carbon, oxygen, iron, and trace metals, but also the ionization states, energy levels, and dynamics of the stellar atmosphere. And these spectral lines, appearing as dark absorption features or bright emission bands, serve as gateways into understanding stellar life cycles, from formation in molecular clouds to nuclear fusion in cores, from expansion into red giants to eventual demise as white dwarfs, neutron stars, or black holes. And the patterns of these lines, their widths, shifts, and asymmetries, provide insight into rotation rates, convective turbulence, stellar winds, and surface magnetic activity, all while allowing precise measurement of radial velocities via the Doppler effect, which not only informs us about individual stellar motion, but also the large-scale rotation and kinematics of galaxies, revealing the presence of unseen matter such as dark matter, whose gravitational influence subtly warps the motions of stars without emitting light itself. And as spectroscopy extends beyond visible wavelengths into ultraviolet, infrared, X-ray, and radio bands, it uncovers processes invisible to the naked eye, from hot ionized plasmas to cold molecular clouds, from accretion disks around compact objects to jets streaming across light years, allowing astronomers to reconstruct the life histories and interactions of stars, clusters, and galaxies, while simultaneously revealing the chemical enrichment of the cosmos, the distribution of heavy elements forged in stellar cores and supernovae, which seed future generations of stars and planets, establishing the continuity of cosmic evolution. And this understanding allows scientists to trace galactic archaeology, reconstructing the formation history of the Milky Way and other galaxies by comparing spectra of stars of different ages, metallicities, and kinematic properties, identifying remnants of past mergers, accreted dwarf galaxies, and stellar streams that encode billions of years of cosmic events, while also providing clues about star formation rates, initial mass functions, and the impact of environment on stellar evolution. And at the scale of individual stars, spectral analysis informs models of internal structure, energy transport, and fusion rates, while revealing surface phenomena such as sunspots, flares, and oscillations, which in turn affect planetary atmospheres, climate, and habitability. And in binary and multiple star systems, spectra disentangle overlapping light to measure masses, orbital periods, and interactions, enabling precise tests of stellar evolution theories, and providing laboratories for understanding mass transfer, tidal effects, and the limits of nuclear burning. While in extreme systems, such as X-ray binaries, cataclysmic variables, and pulsars, spectroscopy reveals the energetic mechanisms that drive jets, accretion, and explosive phenomena, linking microscopic processes like ionization and radiation transport to macroscopic astrophysical structures and dynamics. And as we extend spectroscopy to integrated light from galaxies, the combined spectra of billions of stars reveal average metallicities, star formation histories, ages, and kinematics, allowing classification into elliptical, spiral, or irregular types, and identification of active galactic nuclei, starbursts, or quiescent systems, while mapping chemical abundances and velocity dispersions across spatially resolved regions uncovers the processes of feedback, enrichment, and galactic evolution, creating a layered, multi-dimensional view of how stars and galaxies evolve in concert with the universe. And these spectral investigations also illuminate cosmological phenomena, as absorption lines in quasar spectra trace intergalactic gas, filaments, and intervening galaxies, mapping the large-scale structure of the universe, the distribution of baryonic matter, and the evolution of elements over cosmic time, while redshift measurements encode expansion history, revealing the age, growth, and dynamics of the cosmos, and the careful comparison of spectra across distance, time, and environment allows scientists to identify trends, anomalies, and extreme cases, from metal-poor population stars that preserve primordial conditions to hypervelocity stars escaping galaxies, while detecting rare isotopes and transient events, such as supernovae and kilonovae, which illuminate the synthesis of heavy elements via rapid neutron capture, demonstrating that every photon carries a story of nuclear, chemical, and dynamical evolution across scales, linking quantum-level processes in atomic nuclei to galaxy-wide dynamics and cosmic chemical evolution. And as astronomers refine spectral models using advanced computational tools, radiative transfer simulations, and machine learning techniques, they increase precision in determining stellar parameters, uncover hidden companions, and predict future evolution, while also providing critical inputs for planet detection, habitability studies, and the search for life, as stellar radiation shapes atmospheres, drives photochemistry, and influences climate stability. And this awareness underscores the interconnectedness of stellar and planetary physics, as light and matter interact to sculpt environments across space and time, from the subtle absorption of starlight in a planetary atmosphere to the energetic outflows that regulate star formation and galactic evolution, all encoded within spectra, which serve simultaneously as diagnostic tools, historical records, and aesthetic manifestations of cosmic beauty, because each color line and gradient reflects fundamental physical laws operating over scales far beyond human intuition, inviting both scientific inquiry and contemplation. reminding us that the universe communicates through light, that matter imprints its signature on radiation, and that the careful study of these signatures unveils the deep structure, composition, dynamics, and history of everything from individual stars to the largest cosmic structures, while fostering a sense of connection, wonder, and understanding, as we recognize that every spectral line represents a chain of interactions spanning nuclear reactions, atomic transitions, photon propagation, and gravitational influence, linking the microcosm to the macrocosm, the instantaneous to the eternal, and observation to insight, and ultimately, stellar spectra offer a window into the invisible, a bridge between human perception and the underlying physical reality, a map of the universe written in light, whose careful interpretation allows us to read the story of creation, evolution, and connection that stretches from the smallest atomic transitions to the grandest galactic arcs, revealing that the cosmos is at once knowable, profoundly interconnected, and breathtakingly beautiful, a universe in which every photon, every absorption line, every emission feature, carries information, history, and aesthetic resonance, providing both a laboratory for scientific exploration and a canvas for human imagination, reflection, and awe, demonstrating that understanding the universe in its entirety requires attention to the subtle, the intricate, and the continuous interplay of light, matter, and motion across all scales, a continuum in which stellar spectra serve as essential, unifying threads, allowing us to trace the rhythm, chemistry, and dynamics of the cosmos while marveling at the beauty inherent in its intricate, luminous patterns. The cosmic microwave background, or CMB, represents the oldest light in the universe, a relic from roughly 380,000 years after the Big Bang, when the primordial plasma cooled enough for photons to decouple from matter and travel freely through space, and this faint radiation, now stretched into microwave wavelengths by cosmic expansion, permeates the universe uniformly, providing a snapshot of conditions at the moment of recombination, encoding the initial density fluctuations that would later grow into galaxies, clusters, and the large-scale structure we observe today. And the study of the CMB allows scientists to measure fundamental cosmological parameters with extraordinary precision, from the overall curvature of space to the relative proportions of dark matter, dark energy, and ordinary baryonic matter, as well as the rate of expansion, known as the Hubble constant, while tiny anisotropies in temperature and polarization reveal the seeds of structure, mapping over and under dense regions that correspond to the scaffolding of the cosmic web, and by analyzing these minute variations with satellites such as KIOB, WDRUMAP, and Planck, astronomers can reconstruct the physics of the early universe, testing predictions of inflation, quantum fluctuations, and the interplay between radiation, matter, and gravity, while constraining models of fundamental particles, neutrino properties, and potential deviations from standard cosmology. And the CMB's uniformity and minute deviations highlight the remarkable balance between homogeneity and anisotropy in the primordial universe, showing that while the cosmos began in near-perfect equilibrium, tiny quantum fluctuations were amplified to produce the vast complexity we see today, and these fluctuations manifest as temperature differences of only a few parts in 100 Zollsed, yet they encode the blueprint of cosmic structure, providing a direct link between microphysical processes at the quantum scale and the evolution of galaxies and clusters over billions of years. And the polarization of the CMB further reveals information about the early universe, including the imprint of gravitational waves, the scattering of photons off electrons, and the alignment of density perturbations, allowing for tests of models of inflationary expansion and primordial gravitational effects, while cross-correlation with large-scale structure and lensing measurements enables mapping of dark matter distribution and the integrated growth of cosmic structures over time, providing a dynamic view of the universe's evolution from near-uniform plasma to the intricate web of filaments and voids observed today, and the spectrum of the CMB, an almost perfect blackbody, offers constraints on energy injection processes, interactions with hypothetical particles, and deviations from standard physics, showing that any exotic processes in the early universe must be subtle, leaving behind only small, detectable fingerprints in the microwave background. And as we consider the cosmological significance of the CMB, it becomes clear that this faint afterglow serves not merely as a relic, but as a unifying thread connecting the birth of the universe, the evolution of matter, and the large-scale architecture of space-time, allowing for tests of general relativity, alternative gravity theories, and the properties of dark energy, while providing a benchmark for numerical simulations, structure formation models, and predictions of galaxy and cluster statistics. And the observation of the CMB also teaches us about the transparency and opacity of the early universe, as the decoupling era marks the transition from a dense, ionized plasma that trapped photons to a transparent cosmos, in which radiation could travel freely, a process that shapes our understanding of recombination physics, atomic transition rates, and the interplay of temperature, density, and expansion rate in governing the behavior of matter and light. And beyond its scientific value, the CMB holds philosophical and aesthetic significance, representing a direct connection to the origin of the universe, a pervasive, gentle hum of photons stretching across the cosmos, invisible yet ubiquitous, carrying the imprint of creation itself, and its detection and mapping require extreme technological sensitivity, ultra-cold detectors, precision calibration, and careful mitigation of foreground contamination from galactic dust, synchrotron emission, and point sources, demonstrating both the ingenuity of human observation and the subtlety of cosmic signals, while advances in microwave technology, superconducting detectors, and cryogenics have allowed us to probe the CMB's properties in ever finer detail, measuring polarization modes, lensing effects, and spectral distortions, all of which provide constraints on the physics of inflation, neutrino masses, and the possible presence of primordial magnetic fields. And by integrating these measurements with observations of large-scale structure, type I supernovae, baryon acoustic oscillations, and gravitational lensing, a consistent, self-reinforcing model of the universe emerges, showing the interconnectedness of early universe physics, matter evolution, and cosmic expansion. And the CMB also provides a temporal baseline against which all cosmic events are measured, establishing an absolute frame of reference for distance, redshift, and time, while encoding information about the initial conditions, symmetry breaking, and particle interactions that govern the primordial cosmos, allowing physicists to probe conditions far beyond the reach of terrestrial laboratories, from temperatures of thousands of Kelvin to energy scales, approaching grand unification, linking the faint microwaves we detect today to phenomena occurring at quantum scales and energies, far exceeding anything on Earth. And as the CMB photons traverse the expanding universe, they interact weakly with matter, preserving a nearly pristine record of the early universe. Yet their paths are subtly deflected by gravitational lensing, revealing the distribution of dark matter and the geometry of space, time. And these tiny deflections allow cosmologists to reconstruct mass maps, study cluster formation, and test models of structure growth, while maintaining the overall isotropy and uniformity that confirm the predictions of standard cosmology. And the study of CMB anomalies, such as the cold spot, hemispherical asymmetry, or alignment of low multipoles, challenges our understanding of cosmic variance, inflationary physics, and possible topological features of the universe, inviting deeper exploration of fundamental principles and the limits of observational cosmology, while inspiring theoretical innovation, numerical simulations, and philosophical reflection on the origin and evolution of cosmic order. And as we contemplate the omnipresent CMB, a faint, all-pervading glow from the dawn of time, we recognize its dual role as both messenger and monitor, preserving the signature of creation while continually informing us about the universe's content, evolution, and large-scale behavior. and this awareness offers both intellectual insight and a profound emotional perspective, situating human life and observation within a vast, slowly evolving galaxy, connected through photons that have traveled billions of years across expanding space to reach our instruments, whispering the story of the universe's infancy, growth, and enduring structure, while illustrating the unity of physics across scales, from quantum fluctuations in the primordial plasma to the large-scale distribution of galaxies, clusters, and filaments, and ultimately, the CMB provides a tangible, measurable, and continuous connection to the very beginning, a cosmic afterglow that encodes the principles of creation, the conditions for structure formation, and the elegant simplicity of the laws governing energy, matter, and space. Time, a silent, omnipresent witness to the universe's birth, expansion, and persistent, harmonious evolution, and as we observe, analyze, and contemplate it, we gain not only scientific knowledge, but also a sense of continuity, perspective, and cosmic serenity, recognizing that the universe, in its vastness and subtle complexity, carries a memory of its own origins, a gentle, expansive, and enduring echo of creation that underlies all subsequent events, structures, and phenomena, and by studying the CMB, we bridge the gap between observation and origin, between human understanding and cosmic reality, allowing insight, awe, and reflection to coexist with rigorous science, revealing the deep, persistent, and beautiful architecture of the universe from its very first light. Interstellar dust, often overlooked because it is invisible to the naked eye and absorbs only a tiny fraction of starlight, plays a fundamental role in shaping the structure, evolution, and visual character of galaxies, acting as both a medium and a moderator of cosmic processes, as these microscopic grains, composed of silicates, carbonaceous compounds, ice, and metallic inclusions, drift through space, slowly moving under the influence of radiation pressure, magnetic fields, and the gentle tug of gravity, and their presence affects the temperature, chemistry, and ionization state of surrounding gas, facilitating the formation of molecular clouds that serve as stellar nurseries, while their ability to scatter, absorb, and emit light creates the intricate interplay of illumination and shadow that defines the appearance of spiral arms, nebulae, and galactic disks, and although each grain is minuscule, the collective effect of trillions of particles across vast regions produces significant opacity in the ultraviolet and visible spectrum, reddening starlight and shaping the observable color gradients of galaxies, which in turn informs astronomers about star formation rates, dust density, and the life cycle of matter within a galaxy, and the role of dust extends beyond mere optical effects, as these particles provide surfaces for chemical reactions that generate complex molecules, including water, carbon monoxide, and organics, while shielding fragile molecules from destructive ultraviolet radiation, a process essential for the chemistry that eventually leads to planets and potentially life. And as dust grains collide, coagulate, and fragment, they evolve in size, shape, and composition, gradually building up larger aggregates that can seed planetesimals and protoplanetary disks, linking the presence of dust to planetary system formation, while also contributing to the enrichment of the interstellar medium, with metals and heavier elements, recycled from previous generations of stars through stellar winds and supernova ejecta. And this continuous cycle of destruction, formation, and redistribution illustrates the dynamic equilibrium of galactic ecosystems, where dust is both sculptor and witness, shaping structure while carrying the memory of prior stellar activity, while also regulating the thermal balance of the interstellar medium by absorbing high-energy photons and emitting infrared radiation, thereby influencing the collapse and stability of molecular clouds, star formation rates, and the distribution of energy throughout the galaxy, and these interactions create subtle visual textures in deep space images, from dark lanes threading across the Milky Way to wispy silhouettes in nebulae, demonstrating that what seems absent or dark is in fact active, dynamic, and formative, guiding the flow of light, energy, and matter, and in this way, Dust becomes a bridge between the microscopic and macroscopic, linking the chemistry of individual grains to the formation of stars, planetary systems, and galactic structures, while also providing astronomers with a tool to trace the physical conditions, density waves, and magnetic environments in distant regions, as observations in infrared, submillimeter, and radio wavelengths reveal thermal emission, polarization, and scattering effects, mapping both the quantity and alignment of dust grains, and this mapping informs models of turbulence, gas dynamics, and cosmic magnetism, illustrating how minute components exert outsized influence across astronomical scales, while the distribution of dust also serves as a chronological record, retaining evidence of past supernovae, stellar winds, galactic mergers, and accretion events, allowing researchers to reconstruct the history of star formation, feedback, and chemical enrichment over billions of years, and the interaction of dust with light creates phenomena such as reflection nebulae, dark nebulae, and extinction lanes, all of which guide the eye along gentle cosmic contours, revealing not only the locations of hidden structures, but also the processes shaping them, while the gradual absorption and scattering of photons reminds observers that even subtle, persistent influences can sculpt and direct the evolution of vast systems over time, and in the presence of intense radiation fields, dust can be destroyed or modified, sublimated by ultraviolet light, or shocked by supernova blast waves, illustrating that these particles are both resilient and fragile, their life cycle intimately connected with the life and death of stars, while the replenishment of dust through stellar mass loss ensures a continuous, balanced ecosystem, highlighting the self-regulating nature of galaxies, in which creation and destruction coexist in dynamic harmony. And as we extend our attention to the broader impact of dust, we see that it governs the visibility of distant galaxies, moderates the propagation of light across the universe, and even affects measurements of cosmological parameters, necessitating precise modeling and calibration in observational astronomy to account for extinction, reddening, and infrared emission, while also providing opportunities for new discoveries as dust and shrouded regions reveal hidden star clusters, protostellar systems, and molecular complexes when observed in appropriate wavelengths, demonstrating the interconnectedness of observational technique, cosmic structure, and physical process. And philosophically, dust offers a meditation on the significance of small, often invisible components, whose cumulative effects shape environments, histories, and perceptions. A principle echoed in human experience where subtle forces, background influences, and incremental actions accumulate to produce profound outcomes. And just as interstellar dust molds galaxies without overt display, it reminds us that the quiet, persistent, and distributed exertion of influence can be transformative, guiding systems toward coherence, nurturing complexity, and enabling cycles of creation and renewal. And as we contemplate the intricate filigree of dust silhouetted against glowing nebulae, winding through spiral arms, and diffusing starlight, we are drawn to recognize a universe in which the unseen is active, the subtle is formative, and the microscopic participates fully in cosmic evolution, providing both a practical tool for astrophysics and a poetic illustration of interconnectedness, continuity, and enduring rhythm, where every particle, no matter how small, contributes to the luminous tapestry, structural balance, and ongoing creation of the cosmos. And by studying dust, we uncover not only the mechanics of star and planet formation, but also a model for understanding how hidden, quiet, and persistent processes shape large, complex systems, offering insight into the interplay between light and dark, formation and decay, and the patient, cumulative effects of countless small agents acting in concert over billions of years. And ultimately, interstellar dust teaches that the universe is not solely defined by the bright, energetic, or dramatic, but equally by the quiet, diffuse, and invisible components whose influence is continuous, pervasive, and profoundly creative, a cosmic sculptor whose subtle guidance shapes the visible and invisible alike. ensuring that galaxies evolve gracefully, stars are born, planets form, and the universe maintains its intricate, dynamic balance across space, time, and scale, inviting both scientific inquiry and reflective awe at the harmony arising from the interplay of countless microscopic agents within a vast, enduring cosmos.